How light decides when to act like matter. You might be looking at a wall right now. Or perhaps your desk, or the back of your hand. And you likely believe you see it because light is simply bouncing from it to your eye. A straightforward reflection. But that isn't the whole story. For every particle of light that meets that surface, a quiet, instantaneous event takes place. A kind of choice that seems to blur the line between light and solid matter. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is a journey into that choice. A choice that unfolds trillions of times each second, all around you, just so the world can appear. It begins with a simple assumption that feels like common sense but is fundamentally incomplete, and it ends in the quiet, strange, and deeply ordered world of quantum mechanics. First, let's look at that assumption. If you shine a light into a mirror, you see a bright, clear spot reflecting back. The image is clean, the reflection predictable. Now, shine that same light onto a book, or a piece of wood, or the fabric of your sleeve. What you see is the object itself. You see its texture and its color. But you do not see a reflection of the light source. The light arrives at the surface and seems to stop. It illuminates the object, but it does not return in that same orderly way. The common belief is that light only truly reflects from shiny things. That mirrors are special, while other objects just absorb the light. But if that were true, if a dull surface did not reflect light, you wouldn't be able to see it at all. The very act of seeing your hand proves it is reflecting light toward you. So what is happening? Why does light seem to follow two different rules? This is not just a simple curiosity. It is a profound question. And the answer asks us to quietly let go of what we think we know about how light, matter, and reality itself seem to work. The classical expectation. A world of simple bounces. For a long time, our understanding of light was beautifully simple. It was a world governed by what we now call classical physics, a set of rules established by thinkers like Isaac Newton. In this classical view, light's meeting with a surface was like a game of cosmic billiards. Imagine light as a stream of incredibly small particles. When this stream strikes a very smooth surface, like a mirror, something predictable happens. Each particle hits the surface and bounces off at a precise angle. The rule is simple. The angle of its approach equals the angle of its departure. Every particle follows this with perfect consistency. Because all the particles hit a surface where every point is aligned, they all bounce away in the same direction, holding their formation. This is called specular reflection. The result is a clear, crisp image. You see your reflection because light from your face travels to the mirror, bounces off in a coherent, organized way, and enters your eye, allowing your brain to reconstruct the image. It is orderly, neat, and it makes intuitive sense. Now, what about a surface that isn't shiny? In the classical view, these surfaces are simply rough. On a microscopic level, they are a landscape of small peaks and valleys. When the stream of light particles arrives at this terrain, the game changes. Each particle still obeys the law of reflection, but the surface, each one hits points in a different direction. One particle might strike the side of a microscopic peak and bounce left. The one beside it might land in a valley and bounce up. The result is that the organized stream of incoming light scatters in every possible direction. This is called diffuse reflection. The light is still reflecting, but it is going everywhere. This is why you can see a wall from anywhere in a room. Light particles are bouncing off it in all directions, and no matter where you are, some of them will find your eyes. But because the light is scattered, it cannot form an image. Your brain simply registers the wall's presence and its color. And finally, there was absorption. In the classical model, when light hits a dark object, it is as if the particle gets stuck. Its energy is not reflected, it is transferred to the material, usually as heat. This is why a dark surface gets warmer in the sun than a light one. The dark surface is absorbing more of the light's energy, while the light surface is reflecting most of it away. So, the classical picture was complete. Specular reflection for shiny things, diffuse reflection for rough things, and absorption for dark things. It was a tidy model that explained much of what we saw. And for a very long time, it was believed to be the whole truth. But it was not. There were clues, quiet phenomena that did not fit, which hinted that something was missing from this picture. The weird evidence, the cracks in the classical world. The classical model of the universe worked so well. But science is a process of constant questioning, of gently probing the edges of our understanding. And as physicists began to look more closely at the behavior of light, the classical model began to show small cracks. It started with a phenomenon known as the photoelectric effect. In the late 19th century, it was discovered that when light shines on a piece of metal, it can sometimes knock electrons loose. This seems to make sense, even classically. Light carries energy, and enough energy should be able to dislodge a particle. The classical prediction was straightforward. The brighter the light, the more energy you are using, and so the more energetic the electrons that get kicked off should be. But that is not what the experiments showed. Physicists found that the energy of the electrons did not depend on the brightness of the light at all. An intense light knocked off more electrons, but not faster ones. This was unexpected. It defied the logic of cause and effect as it was then understood. The only thing that changed the asterisk energy of the electrons was the color, or frequency, of the light. Blue light knocked off more energetic electrons than red light. In fact, below a certain frequency of light, no matter how bright it was, no electrons were ejected at all. It was as if the light's energy arrived in discrete packets. A single packet of red light did not have enough energy to free an electron, so it did not matter if you sent 1 or 1 billion. But a single packet of blue light did. This was the first clear sign that light wasn't just a continuous wave. It was acting like a particle. A single particle of light, a photon would collide with a single electron. If the photon had enough energy, the electron was freed. If not, nothing happened. This was the work for which Albert Einstein received the Nobel Prize. He proposed that light energy is quantized. It comes in these particle-like packets. This idea explained the photoelectric effect perfectly, but it created a problem. For over a century, another experiment had stood as clear proof that light was a wave the double-slit experiment. Imagine a wall with two thin, parallel slits. If you throw solid objects at it, like grains of sand, you expect to find two piles on the other side. Now, imagine doing this with waves in water. When a wave hits the two slits, it splits into two smaller waves that interfere with each other. Where their crests meet, they reinforce. Where a crest meets a trough, they cancel out. The result on the back wall is not two simple lines, but a pattern of many bands. This interference pattern is the undeniable signature of a wave. And when physicists performed this experiment with light, that is exactly what they saw. An interference pattern. Unambiguous proof that light is a wave. So, which is it? The photoelectric effect seems to prove light is a particle. The double-slit experiment seems to prove it is a wave. It cannot be both a localized object and a spread-out disturbance at the same time. This was not just a crack in the classical model, it was a chasm. Reality was showing two contradictory faces. This dual nature, this wave-particle duality is the key to understanding how light decides what to do when it meets a wall. Introducing the suspect, the ghost in the machine. The conflict was absolute. Light was a wave. Light was a particle. Both were supported by clear experimental evidence. It took a new generation of physicists to develop a new way of thinking, which came to be known as quantum mechanics. And its central conclusion was this: the question, is light a wave or a particle, is the wrong question to ask. Quantum mechanics tells us that light is neither purely a wave nor purely a particle. It is something else, an entity that holds the properties of both. It only appears as one or the other depending on how we interact with it. Let us return to the double-slit experiment. We send light through the slits and get an interference pattern, the signature of a wave. We can turn the light source down so low that only one single photon is sent out at a time. It travels, passes through the apparatus, and makes a single dot on a detector screen. A particle-like impact. We fire another photon. It lands elsewhere. Then another, and another. We let this run for hours, firing single, isolated photons. At first, the dots on the screen seem random. But as thousands of these individual impacts accumulate, a pattern begins to emerge. It is the interference pattern. Think about what this means. Each photon was fired alone. There was nothing for it to interfere with. And yet, the final pattern is the signature of two waves interfering. The only way to explain this is to accept that the single photon, traveling as a kind of wave of probability, went through both slits at the same time. It interfered with itself. This is the heart of quantum mechanics. Before it is measured, a particle like a photon does not exist at a single point. It exists in a state of superposition, a haze of all possible outcomes described by a mathematical tool called a wave function. When we fire the photon, its wave function spreads out, passes through both slits, and the two resulting paths of the wave function interfere. This interference dictates the probability of where the photon will eventually be found. When the wave function hits the detector screen, the interaction forces it to choose a single location. The superposition collapses, and we see a single dot. Naturally, physicists wanted to know which slit the photon really went through. So they set up a detector at the slits, a device to tell them whether a photon passed through the left or the right. They run the experiment again, one photon at a time. The detector works. This photon went left. The next went right. They now know the path of every photon. But when they look at the pattern on the back screen, something has changed. The interference pattern is gone. In its place are two simple stripes, just as if they were firing grains of sand. The very act of observing which path the photon took forced it to behave like a particle. The wave behavior, the superposition, the self-interference, vanished. The act of measurement fundamentally alters the outcome. So, light does not have a fixed nature. Its identity is fluid. When it travels unobserved, it explores all possibilities like a wave. When we force an interaction, when it hits a detector or an atom in a wall, it has to collapse from a wave of many possibilities into a single reality. It must act like a particle. This is not a conscious choice, of course. But the universe is built so that the interaction between the quantum world and our world forces a resolution. A decision must be made. The investigation, reflection, scattering, and the photon's choice. Now we can return to our original question armed with the tools of quantum mechanics. Why does a mirror create a reflection, while a wall does not? The classical answer was surface roughness. The quantum answer is more subtle. And it is a story of probability and the sum of all possibilities, a concept rooted in the deep mathematics of quantum electrodynamics, or QED. Let's begin with the mirror. According to QED, when a photon travels from a source to a mirror and then to your eye, it does not take a single straight path. In its unobserved, wave-like state, it takes every possible path. It tries them all. For each path, there is a corresponding probability. For a smooth mirror, the paths clustered around the classical path, where the angle of approach equals the angle of departure, all take almost exactly the same amount of time. This means their probabilities add up and reinforce each other. But for the strange paths, a long loop to the edge of the mirror, for instance, the travel times are all different. Their probabilities are out of sync and, when added together, they cancel each other out. The result is that the only paths that contribute are the ones right around the neat, classical path. This overwhelming probability is what creates the clean, coherent process of specular reflection. It is not that photons are following a single rule. It's that the probabilities of all the other things they could do effectively erase each other, leaving only the reflection we see. Now, let's turn to the wall. On a microscopic level, a wall is a chaotic arrangement of atoms. Its surface is not smooth. When a photon's wave function meets this surface, the concept of taking every path still applies, but now there is no single, neat family of paths that all have the same travel time. Almost every path has a wildly different length. This means that the probabilities no longer reinforce one another in a single direction. Instead, the probabilities are scattered. There is some chance the photon will bounce left, some chance it will bounce right, and some chance it will come back toward you. This is diffuse reflection at the quantum level. The reason you cannot see your reflection in a wall is that there is no coherent reinforcement of probabilities to form an image. The information is scrambled because the surface itself is scrambled. But what about the choice to be reflected at all, or to be absorbed? This is about energy. The electrons in an atom are restricted to specific energy levels. To jump from a lower level to a higher one, an electron needs a precise amount of energy. When an incoming photon arrives, it carries an amount of energy determined by its color. One possibility is that the photon's energy does not match any of the allowed energy jumps for the electrons in the atom. In this case, the atom cannot permanently keep the photon's energy. The photon is effectively re-emitted. This is the essence of reflection. The other possibility is that the photon's energy is a perfect match. The electron can then absorb the photon's energy completely and leap to a higher level. When this happens, the photon ceases to exist. It has been absorbed. The electron usually cannot stay in this excited state for long and will fall back down. Often, it releases this energy not as a single photon of light, but through tiny vibrations, which we perceive as heat. This is why a dark t-shirt gets hot. The dyes in the fabric have electron energy levels tuned to absorb the energy of photons across the visible spectrum. The color of an object is determined by which photon energies its atoms are willing to absorb and which they are forced to reject and re-emit. A green leaf is green because the chlorophyll absorbs blue and red light and reflects green light. The decision is a complex quantum event, a probabilistic outcome determined by the combination of all possible paths and the matching of energy. You might be thinking that this is all impossibly complex. The idea that this happens for every particle of light, on every surface, all the time, just so you can see the room around you, is difficult to hold in the mind. We've journeyed from a simple wall to the foundations of quantum reality. If your mind feels a little stretched right now, that is a good thing. It means you're grappling with how truly different the universe is from our everyday experience of it. If you find this kind of quiet exploration into science helps you see the world differently, consider liking the video and subscribing to the channel. It helps us continue to unravel these stories. The reveal, a universe of probability. So, how does light decide when to act like matter? The answer is both simple and a quiet humbling of our intuition. Light does not decide anything. The decision is an illusion. What we perceive as a choice is the outcome of an interaction, governed by the mathematics of quantum probability. At its fundamental level, reality appears to be probabilistic, not deterministic. An unobserved photon is a wave of potential, a superposition of every possibility. The decision happens at the moment of measurement. And measurement here means any interaction that forces the quantum system to resolve into a single state. When a photon's wave function meets an atom in the wall, that is a measurement. The interaction forces the wave of potential to collapse. Does it act like a particle? Yes, because the interaction is localized. It happens at a specific atom, at a specific point in time. This is particle-like behavior. Does it reflect or get absorbed? This is a question of energy and probability. The structure of the atom determines the odds. It is like rolling a quantum die. The structure of the material loads the die, but the outcome of any single roll is random. Does it reflect specularly or diffusely? This is a question of geometry and interference, the outcome of the sum over all possible paths. For a smooth surface, the paths creating a neat reflection reinforce each other, making that outcome a near certainty. For a rough surface, the paths are jumbled, and the probability is scattered. Light is always acting according to the laws of quantum mechanics. We, as large-scale observers, only see one aspect of its nature at a time because our very act of interaction forces a collapse. The decision to act like matter is not a choice made by the light. It is a demand placed upon the light by its interaction with matter. This is one of the most established ways to understand the event, known as the Copenhagen interpretation, though physicists still explore other possibilities for what this moment of collapse truly means. We began with a simple question: how do you see a wall? We learned it is about a constant, quiet storm of quantum events happening all around us. The idea that light only reflects from shiny surfaces is a misunderstanding of how we see anything at all. Every non-luminous object you have ever seen, you have seen because of diffuse reflection. You see the world because light, in its particle aspect, is constantly scattering from the chaotic surfaces of everything, sending a cascade of photons in all directions. The mirror is the exception. It is the one place where quantum probabilities align with such perfection that an image can form. But the wall is the truth. The wall is a quiet testament to the probabilistic and deeply ordered nature of light's interaction with matter. Every time you open your eyes, you are part of this process. You are collapsing wave functions, forcing countless photons to abandon a state of infinite possibilities and resolve into a single particle, here, now. The interaction of their energy with the atoms of the world decides their color. The sum of their possible paths decides their texture. The line between light and matter is not just blurred, it is contextual. They are two sides of the same quantum reality. And the decision of when to show which face is simply the universe's way of resolving the fuzzy, probabilistic quantum realm into the definite, classical world we experience. So the next time you look at a simple wall, take a moment. Appreciate the quiet complexity of what is taking place. You are not just seeing light bounce. You are witnessing a continuous, silent process. A trillion tiny outcomes that, taken together, paint the world. And that leaves a final, open question to carry with you. If the universe is only forced into a definite state when it's observed, what does it look like when nothing is watching? The quantum glitch that breaks reality. Have you ever considered what it means to see something? The simple act of light reflecting from an object and entering your eye feels passive, as if we are only watching a world that would continue on, unchanged, without us. It is a deeply held human intuition. But what if for the smallest parts of our universe, this is not true? What if for the fundamental pieces of reality, the simple act of being seen changes what is there? What if it alters their behavior, their past, and their future in a way that seems to challenge our understanding of what it means to exist at all? There is an experiment in physics that reveals a paradox so profound, so quietly strange, that it forces us to reconsider the nature of the world. The physicist Richard Feynman once said that this single experiment contains the very heart of quantum mechanics, a mystery that, if understood, could explain the deepest strangeness of the natural world. And the most unsettling part? It suggests that reality itself may not be as solid or as definite as it seems. The world, at its most fundamental level, might be a realm of quiet possibilities, waiting for an observation to give it form. Today, we are going to look behind the curtain. We will walk through the experiment, step by step, and arrive at the moment where our familiar reality seems to dissolve. This is the story of the double-slit experiment, and the quiet connection between looking at the world and creating it. The familiar world of particles. Before we enter the quantum world, let us begin on solid ground. In the world we think we know, the predictable, classical world. Imagine you have a device that fires small, solid pellets, like tiny grains of sand. In front of you is a wall, and in that wall, we have placed a barrier with two narrow, vertical slits cut side by side. Your task is simple. You stand back and spray these pellets toward the two slits. What would we expect to see on the wall behind the barrier? The answer feels like common sense. Some pellets will hit the barrier and stop. Some will go through the left slit, and others will go through the right. The pellets that go through the left slit will land on the wall directly behind it. The ones that go through the right slit will land on the wall directly behind that one. If we do this long enough, we will find two distinct vertical stripes on the back wall, one perfectly aligned with each slit. A graph of where they landed would show two peaks, one for each opening. There is nothing mysterious here. This is a world of particles. Solid, tangible things that follow definite paths and exist in one place at a time. A single pellet cannot go through both slits at once. It goes through one, or it goes through the other. This is our baseline for reality. It is how we expect solid objects to behave, no matter how small. From planets orbiting a star to a ball thrown through the air, the universe at this scale is governed by a set of reliable rules. Objects have a definite position. They follow a clear path. This is the universe described by Isaac Newton, a view that for centuries seemed complete. If you fire a single object, you know it can only go through a single opening. If you close one of the slits, you get one stripe. If you close the other, you get the other stripe. With both open, you get the sum of the two. It is simple addition. It is important to hold this idea, because the foundation of our normal world is about to be shaken. The lesson is this: particles are distinct things. They arrive at a screen as individual impacts, and they build a pattern that is a direct map of the openings they passed through. Simple, logical, and deeply intuitive. Now, let us change what we are firing. The world of waves. Let us set aside the pellets and imagine a calm, still pool of water. Instead of a back wall, there is a beach. In place of the barrier with two slits, we have a long breakwater with two small gaps. Now, instead of firing particles, we will create waves. We can use a machine that rhythmically dips into the surface, sending out a continuous train of ripples. These ripples spread out from their source, moving across the water. When the wave front reaches the breakwater, most of it is blocked. But at the two gaps, something else happens. Each gap becomes a new source of waves. A new set of circular ripples spreads out from the left gap, and another set spreads out from the right. These two new sets of waves travel toward the beach, and as they do, they begin to overlap. They interfere with each other. What happens when two waves interfere? In some places, the peak of a wave from the left slit will meet the peak of a wave from the right. At that point, they add together, creating a much larger wave. This is called constructive interference. In other places, the peak of a wave from the left will arrive at the same moment as the trough of a wave from the right. When this happens, they cancel each other out. The water at that spot becomes still. This is called destructive interference. So what does the pattern on the beach look like? It is not two simple marks. Instead, we see a striped pattern. There is a central band of high energy where the waves arrived together, then a band of almost no energy where they cancelled out, then another high energy band, and so on, spreading out across the shore. This series of alternating bands is called an interference pattern. It is the unmistakable signature of waves. This phenomenon is all around us. It is what creates the shimmering colors on a soap bubble, and how sound can seem to bend around a corner. Crucially, this pattern can only be created if the wave passes through both slits at the same time. If you block one slit, the interference pattern vanishes. You are left with just a single wave spreading out from the one remaining opening. The interference is a product of the wave being split and then interacting with itself. So we now have two very different results. Particles create two simple bands. Waves create an interference pattern of many bands. The difference is stark, and it gives us a clear way to test the nature of anything. If you want to know if something is a particle or a wave, you send it toward two slits and look at the pattern it makes. Two bands mean it is a particle. An interference pattern means it is a wave. This seemed like a clear, unambiguous dividing line in the physics of our universe. Or so it was thought. The first quantum surprise, light as a wave. For a long time, there was a debate in physics about the nature of light. Isaac Newton believed light was made of tiny particles, but others suspected it was a wave. In the early 1800s, a scientist named Thomas Young decided to settle the question. He performed the experiment we just described, not with water, but with light. In what is now one of the most famous experiments in history, Young shone a beam of light onto a screen with two incredibly narrow slits. He reasoned that if light were made of particles, as Newton thought, he should see two bright lines on the detector screen, just like our pellets. But if light were a wave, it should create the distinctive interference pattern of many bright and dark stripes. He set up the apparatus. A light source, a barrier with two slits, and a screen to observe the result. The light passed through the slits, and when Young looked at the screen, the result was undeniable. He did not see two bands. He saw a series of bright and dark fringes, a perfect interference pattern. The waves of light passing through each slit were interfering with each other. It was a triumphant moment. Light, it seemed, was a wave. For decades, this was the accepted truth. Light was an electromagnetic wave, a disturbance rippling through space-time. The double-slit experiment was the definitive proof. It was taught in physics as a clear demonstration of the wave nature of light. The result was consistent and made sense within the framework of wave physics. It was elegant, logical, and seemed to be the final word. But physics was about to get much stranger. As the 19th century gave way to the 20th, new discoveries began to complicate this tidy picture. Scientists found that shining light on metal could knock electrons loose, but what mattered was the light's color, not its brightness. This could only be explained if light was not a continuous wave, but instead came in discrete packets of energy, what we now call photons. Suddenly, Newton's idea of light particles was relevant again. This created a deep contradiction. How could light be both a wave, as shown by the double-slit experiment, and a particle, as shown by the photoelectric effect? This baffling behavior was named wave-particle duality. Light, and as it would turn out, all matter, seemed to have two different natures. Sometimes it behaved like a distinct particle. Other times, it behaved like a spread-out wave. The question was, how could this be? The double-slit experiment held the key. But to unlock it, scientists had to push it one step further. They had to ask a question so simple, yet so profound, it would begin to unravel our concept of reality. They decided to send the light through one particle at a time. The twist, one particle at a time. This is where the story turns from the interesting to the profoundly strange. This is the part of the experiment that Feynman called the central mystery. Scientists, grappling with the idea that light was made of individual photons, decided to modify Young's experiment. They wondered, if light is a stream of particles, what happens if we send them through the slits one by one? Imagine our device again, but this time it is a special quantum device that can fire a single photon. It is so sensitive that we can ensure only one photon is in the apparatus at any given time. We fire a single photon. It travels toward the slits. It hits the detector screen, making a single, tiny dot of light. There is no wave, no interference, just one particle hitting one spot. We fire another. A second dot appears in a different location. We fire a third, and another. We continue this, thousands of times, firing one single photon, letting it land, then firing the next. What pattern do you expect to emerge on the screen? Common sense suggests we should get the particle pattern. After all, we are firing individual particles. Each photon is a single lump. Since only one is present at a time, it cannot interfere with another photon. It must go through either the left slit or the right slit, just like a pellet. So, over time, we should see two bands of dots build up on the screen. Anything else would seem impossible. A single particle cannot create a wave pattern. A wave needs to go through both slits at once to interfere with itself. A particle cannot do that. So the experiment was run. The first photon lands as a single dot. The second, a dot somewhere else. At first, the impacts look random. Dots appear all over the screen with no clear order. But slowly, painstakingly, as thousands of these individual impacts accumulate, an impossible picture begins to emerge. It is not two bands. Slowly, dot by single dot, the interference pattern builds on the screen. The very same pattern of multiple bright and dark fringes that appeared when we sent a continuous wave of light through the slits. Let us pause and absorb the quiet impossibility of this result. We are firing single particles. One photon leaves the device, travels through the apparatus, and hits the screen long before the next is fired. And yet, the pattern that emerges over time is the signature of a wave that went through both slits at once and interfered with itself. How can this be? It is as if each photon, traveling alone, somehow knows about both slits. It seems to pass through both simultaneously, like a wave, interfering with itself. Then, upon hitting the screen, it becomes a particle again, landing in a single spot. But the spot it chooses is governed by the probability wave that went through both paths. The dark fringes of the pattern are areas where a photon will never land, even though those areas would have been accessible if only one slit were open. Opening a second path makes certain places on the screen forbidden. The great physicist Paul Dirac said that each photon interferes only with itself, a statement that captures the paradox without truly explaining it. The photon acts like a wave of possibilities, exploring all available paths. This probability wave is what passes through both slits and interferes. The pattern on the screen is a map of probabilities, showing where the photon is most and least likely to be found. When the photon hits the screen, this wave of possibilities collapses, and the photon appears in a single location, according to those probabilities. This is not just for photons. Scientists have performed this experiment with electrons, and the result is the same. They have even done it with entire atoms and large molecules. Even these solid pieces of matter, when sent one by one, behave like waves, passing through both slits at once to create an interference pattern. The implications are staggering. It suggests that at the fundamental level, reality is not made of solid things, but of waves of probability. An electron is not at any single point until it is measured. Instead, it exists as a field of potential, a superposition of all its possible states, until an interaction forces it to choose one. This leads to an obvious, unavoidable question. The question that leads us to the heart of the mystery. If the particle is going through both slits at once, what if we try to look? What if we spy on it and see which slit it goes through? The glitch, spying on the system. We have arrived at the center of the mystery. We are faced with an impossible result. Single particles, fired one at a time, behave like waves, going through two slits at once to create an interference pattern. The logical next step is to try and catch them in the act. Let's return to our experiment. We have our single photon device, our barrier with two slits, and our screen. But now, we will add a new piece of equipment. We will place a tiny detector right next to one of the slits. This detector will do one simple thing. It will register a small signal every time a photon passes through that specific slit. If the detector signals, we know the photon went through the top slit. If it does not signal, and a dot still appears on the screen, we can deduce it must have gone through the bottom one. This setup gives us what physicists call, which way, information. For the first time, we will know the path each particle took. We can finally know if each photon really goes through only one slit. So, we turn the experiment on. We fire the first photon. Let's say our detector by the top slit signals. A moment later, a dot appears on the screen. We make a note. Photon 1 went through the top slit. We fire another. This time, no signal. A dot appears on the screen. We make another note. Photon 2 went through the bottom slit. We continue this process, firing thousands of photons, one by one. For each and every one, our detector tells us which path it took. We have successfully spied on the particles. We now know that each photon went through either one slit or the other. It did not go through both. But what about the pattern on the screen? Since we know each photon only went through a single slit, it could not have interfered with itself. It behaved like a proper, well-behaved particle. So, we should expect the particle pattern. Two simple bands, one behind each slit. And that is exactly what we see. The moment we look, the interference pattern is gone. It has completely vanished. Instead, we have two simple bands, exactly like the ones we got when firing pellets. Let that sink in. The act of observing which path the photon took forced it to behave like a particle. By simply gathering information about the photon's journey, we destroyed its wave-like nature. It is as if the photon knew it was being watched and chose to behave differently. This is the collapse of the wave function. The moment we measure the photon's position, the moment we know which slit it went through, its wave of potential that was spread across both slits instantly collapses into a single, definite state. It snaps from a wave to a particle. Perhaps our detector is too clumsy. Maybe in the process of detecting, it physically bumps the photon. It's a reasonable thought, and physicists considered it. They designed incredibly gentle ways to measure the path. But the result is always the same. Any interaction that reveals the which way information, no matter how subtle, destroys the interference pattern. If you know the path, there is no interference. If you see interference, you cannot know the path. You can have one or the other, but never both. This fundamental trade-off was given a name by the physicist Niels Bohr. He called it complementarity. The particle nature and the wave nature of an object are two complementary aspects of its reality. They are like two sides of the same coin, and you can only ever see one side at a time. An experiment designed to measure the particle properties prevents you from seeing its wave properties, and vice versa. It is a fundamental law of nature. This is not about a conscious person. The observer in quantum mechanics is any interaction with the environment that records which path the particle took. The detector's memory of the photon's path is what forces the wave to collapse. This has led to even stranger experiments, like the delayed choice quantum eraser. In these, the decision to either keep or discard the which way information is made long after the particle has already hit the screen. The results are just as strange. If the information is kept, no interference pattern forms. If the information is erased before it can be looked at, the interference pattern reappears. This does not mean we are changing the past, but it shows how deeply our concepts of time, information, and reality are connected at the quantum level. It seems the universe does not decide whether a photon was a wave or a particle until the final information is registered. This journey into the heart of quantum mechanics is a deep one, and the double-slit experiment is just the beginning. The principles we've uncovered here are the foundation for new technologies, from quantum computing to new forms of communication. If this kind of quiet exploration into the rules of our universe is something you enjoy, consider liking the video and subscribing to the channel. We have only just begun to scratch the surface of the quantum realm, and the next quiet mystery is just around the corner. The why explanations and implications. So, what does this all mean? What is the universe telling us with this quiet, reality-bending experiment? For nearly a century, physicists and philosophers have debated its meaning, and there is still no single answer. But the experiment points toward a radical rethinking of what reality is. The most common interpretation, known as the Copenhagen interpretation, essentially says that we should stop trying to imagine what the photon is really doing. The question, where was the particle before I measured it, may be meaningless. Before a measurement, the particle does not have a definite position. It exists in a state of all possibilities at once, a superposition. It is both wave and particle, it is going through both slits and neither. It is only the act of measurement that forces this cloud of potential to collapse into a single outcome. In this view, reality is not a fixed thing that we passively observe. Instead, the act of observation plays a role in creating the reality we see. As physicist John Archibald Wheeler put it, we live in a participatory universe. This is a stark departure from the classical worldview. Einstein, famously, disliked this idea. He could not accept that the universe was fundamentally based on chance. His famous quote, "God does not play dice," was a challenge to the probabilistic nature of quantum mechanics. He argued that a particle must have a definite path, even if we do not know it. However, decades of experiments have, so far, not supported his view. It seems the universe really is that strange. The core concept is wave-particle duality. It is not that an electron is sometimes a wave and sometimes a particle. It is that it is a single quantum entity that possesses properties of both. Our classical language of waves and particles is just an approximation. We use those words because they are familiar to us, but the quantum object itself is something else entirely. Something for which we have no good analogy. The experimental setup itself determines which face the quantum entity shows us. If you set up an experiment to ask, "Are you a particle, and which path did you take?" the universe will give you a particle answer. If you set up an experiment to ask, "Are you a wave, and will you interfere?" the universe will give you a wave answer. The question you ask shapes the answer you get. You cannot ask both questions at the same time. This is the principle of complementarity in action. The implications of this are profound. It suggests that the solid world we experience is an emergent property. At the bottom layer, reality is a shimmering, probabilistic foam. The atoms that make up your hand and the chair you are sitting on are all governed by these same strange rules. The only reason we do not see a chair behaving like a wave is due to a phenomenon called decoherence. The constant interaction of a large object with its environment, billions of air molecules and photons of light bouncing off it, is a form of continuous measurement. Each tiny interaction collapses the wave function, pinning the object to a single state so quickly that its quantum nature is washed out. But at its core, the double-slit experiment teaches us a lesson in humility. It tells us that our common-sense intuitions, formed in a world of large objects, fail when we get to the fundamental level. Reality is not what it seems. It is a place of potential and probability, where observation is not a passive act but an intimate part of what happens. Conclusion: we began with a simple question. What happens when you fire something through two slits? We found an answer that defies easy explanation. We found that the universe, at its most fundamental level, operates on rules so strange they sound more like philosophy than physics. The world is not a collection of tiny, solid things. It is a quiet, probabilistic dance between waves of potential and particles of reality. The double-slit experiment reveals what may be the deepest truth of quantum mechanics. The nature of what we observe is tied to how we observe it. A particle, left to itself, is like a ghost, a wave of probability exploring all paths at once. But the moment we look, the moment we ask, "Where are you?" the ghost solidifies, the wave collapses, and reality chooses a state. As Richard Feynman put it, this experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. It is a quiet contradiction in our classical understanding of the world, a seam in the foundation of common sense that reveals a universe underneath that is far more mysterious and interconnected than we ever imagined. It leaves us with a question that science has not yet answered. What is the world, when no one is looking? Einstein's light trick that changed reality. The light that fills a room does so quietly. We see it as a continuous presence, a gentle wash of illumination that makes the world visible. It feels steady, constant, and whole. But this simple experience hides a deeper and stranger reality. What if that smooth, flowing stream of light was, on a level too small to see, arriving in individual pieces? What if the world was not being washed in light, but being touched by countless, separate packets of energy? For a time, this idea seemed like a mistake. An experiment, simple in its design, revealed a quiet contradiction in the foundations of physics. It pointed to a secret about light so unfamiliar that it felt impossible. The rules that described the orbits of planets and the mechanics of machines did not seem to apply. This is the story of that puzzle. It begins with a curious observation and leads to a new way of seeing the world. It is the story of how a young patent clerk in Switzerland, working in his spare time, proposed an idea about light so fundamental it would change our understanding of reality itself. He suggested that at its smallest scale, light stops behaving like a gentle wave and instead arrives in these discrete packets of energy. This discovery is not just a historical detail. It is a principle that works quietly in the background of our modern world, from solar panels on rooftops to the cameras in our pockets. Prepare to see the light around you in a new way. Imagine standing on a shore as a small wave rolls in, washing over your feet. It carries a certain energy. Now imagine a larger wave, a powerful surge of water. You would expect it to push against you with more force. This is intuitive. It is how we understand energy to work. A bigger wave carries more power. For centuries, this was how scientists understood light. A brighter light was simply a bigger, more powerful light wave. A dim light was a smaller, weaker one. The idea was simple and it made sense. Then, an experiment revealed something that did not fit this picture. Scientists shone a beam of light onto a piece of metal and observed that the light could knock tiny particles, called electrons, from the metal's surface. So, they tried making the light brighter. According to the wave theory, a brighter, more intense light wave should strike the electrons harder, sending them away with more speed and energy. But that is not what happened. When they increased the brightness, more electrons were released, but they were not moving any faster. It was as if a small ripple and a large wave both pushed a floating object with the exact same, gentle nudge. It was a puzzle that seemed to run contrary to the laws of physics. This was the quiet contradiction that classical reality could not explain, and its solution would come from the mind of Albert Einstein, who would reveal one of light's deepest secrets. The world of waves, a reality built on ripples. Before we can appreciate the puzzle that faced physics, we first have to understand the world that was about to be reconsidered. At the turn of the 20th century, the scientific community had a quiet confidence in its understanding of light. The prevailing view was that light was an electromagnetic wave. This was not a guess. It was one of the great achievements of 19th-century science. Think of a wave in a familiar sense, like ripples on a pond. When a stone is dropped into water, the energy spreads out in a continuous, expanding circle. The energy moves through the water as a disturbance. A larger stone creates a larger disturbance, a wave with a higher amplitude, carrying more energy. Sound works in a similar way. My voice creates vibrations that travel through the air as pressure waves. A louder sound is a wave with a greater amplitude. In this classical view, energy is continuous, something that flows. For a long time, there had been a debate about the nature of light. Isaac Newton suggested light was made of tiny particles he called corpuscles. But in 1801, a British scientist named Thomas Young performed an experiment that seemed to settle the matter. It is now known as the double-slit experiment. Young shone a beam of light at a barrier with two thin, parallel slits. If light were made of particles, like small grains of sand, you would expect to see two bright lines on a screen behind the barrier. Instead, he saw a pattern of many bright and dark bands. This is what happens when two sets of water waves overlap. Where two crests meet, they create a larger wave, a bright band. Where a crest meets a trough, they cancel each other out, leaving a calm spot, a dark band. Young's experiment was clear evidence. Light behaves like a wave. This wave theory was placed on a firm mathematical foundation in the 1860s by the Scottish physicist, James Clerk Maxwell. In one of the great unifications in science, Maxwell brought together electricity, magnetism, and light. He produced a set of 4 equations describing how changing electric and magnetic fields create each other and travel through space as an electromagnetic wave. When Maxwell calculated the speed of this wave, he found it was the exact, known speed of light. The conclusion seemed inescapable. Light was an electromagnetic wave. The theory explained things beautifully. The colors of the rainbow were simply light waves with different wavelengths. The brightness of the light was determined by the wave's amplitude. A bright light was a tall wave, carrying more energy, while a dim light was a short one. By the late 1800s, this was settled physics. The universe was seen as a grand, predictable machine governed by Newton's laws of gravity and Maxwell's laws of electromagnetism. Physicists felt they were close to a complete understanding of the physical world. There were just a few loose ends to tie up. Or so they thought. They did not know that one of those minor puzzles was about to unravel their picture of reality. A quiet contradiction, the stubborn puzzle. The first sign that something was not quite right with the perfect, wave-driven universe came from a curious observation. In 1887, the German physicist Heinrich Hertz was conducting experiments to prove the existence of Maxwell's electromagnetic waves. During his work, he noticed something peculiar. A spark in his detector seemed to jump more easily when it was illuminated by ultraviolet light from another spark. He documented the effect, but he did not have an explanation for it and moved on, considering it a secondary phenomenon. He had stumbled upon what would become known as the photoelectric effect. When light shines on a material, it can cause that material to release electrons. Following Hertz's observation, other physicists studied this strange behavior. They confirmed the particles being knocked off were indeed electrons. The experiment was simple in concept. Shine a light on a metal plate in a vacuum tube and measure the electrons that come off. This is where the mystery began. Based on the successful wave theory of light, physicists made a set of logical predictions about what should happen. And each of them turned out to be incorrect. First was the question of intensity. In wave theory, a brighter light is a more energetic wave. Everyone predicted that a brighter light should give the electrons a bigger push, making them fly off the surface faster. But when they performed the experiment, they found something astonishing. A brighter light ejected more electrons, but their maximum speed did not change at all. The fastest electrons moved at the same speed, whether the light was bright or dim. From a classical perspective, this was difficult to explain. The second prediction concerned the frequency of the light, its color. According to wave theory, any color of light, if it were bright enough, should be able to knock out electrons. A very bright red light should carry plenty of energy. But the experiments showed something different. The energy of the ejected electrons depended only on the frequency of the light. Blue light, with a higher frequency, produced faster electrons than green light. And for each metal, there was a specific threshold frequency. If you used light with a frequency below this threshold, for instance, red light on a particular metal, nothing happened. It did not matter how bright the red light was. Not a single electron would leave. But if you then switched to a very dim blue light, which was above the threshold, electrons would appear almost instantly. The wave model had no way to explain this. This led to the third failure of the wave theory, the time delay. The classical model imagined light energy being spread out over the entire wave. If you used a dim light, it should take some time for any single electron to absorb enough energy to escape. Scientists calculated this expected delay could be seconds, minutes, or even hours. But when they performed the experiment, they found that as soon as light of the right frequency hit the metal, no matter how faint, electrons were ejected immediately. There was no build-up time. For nearly 2 decades, the photoelectric effect stood as a quiet but persistent contradiction. The most successful theory of light was failing to explain 3 key observations. The rules of reality seemed to be broken. Physics needed someone who could see the world in a different way. A different way of seeing, the light quantum. The new perspective came not from a celebrated professor, but from a 26-year-old patent examiner in Bern, Switzerland. His name was Albert Einstein. The year was 1905, a period that would become known as his annus mirabilis asterisk, or miracle year. While examining patent applications, Einstein spent his free time reconsidering science. In that 1 year, he would publish 4 papers that changed physics, including the one that would win him the Nobel Prize, his explanation of the photoelectric effect. Einstein was aware of the puzzle. But unlike others who were trying to make the wave theory fit the results, Einstein took a step back. He was influenced by the work of another German physicist, Max Planck. In 1900, Planck had found he could solve a different problem related to the light emitted by hot objects only if he assumed energy was emitted in discrete packets, which he called quanta. Even Planck was not entirely comfortable with this. He thought it might be just a mathematical tool, not a description of reality. Einstein, however, took Planck's idea seriously. He made an intellectual leap. What if this was not just about how energy is emitted, but about the nature of light itself? In his 1905 paper, Einstein proposed that light is not a continuous wave, but a stream of these particle-like energy packets. He called them light quanta. Today, we call them asterisk photons. He suggested that a beam of light is more like a series of individual arrivals than a flowing river. This single idea resolved every mystery of the photoelectric effect with a quiet elegance. Let's revisit the 3 paradoxes. First, the mystery of intensity. The classical theory said a brighter light should eject faster electrons. Einstein's model explained why this wasn't so. A brighter light does not mean each packet of light is more powerful. It simply means more packets are arriving per second. The interaction is a series of one-on-one events. One photon hits one electron. The energy an electron receives depends on the energy of that single photon. Increasing the brightness means more photons are arriving, so more electrons are knocked out, but the maximum energy of any single electron remains the same. The puzzle was solved. Second, the role of frequency. Why could a dim blue light do what a brilliant red light could not? Einstein proposed that the energy of a single photon is directly proportional to its frequency. This gave us one of physics' most important equations, E equals hf, where E is the photon's energy, f is its frequency, and h is a fundamental number known as Planck's constant. This simple relationship explained everything. Blue light has a higher frequency than red light, so a photon of blue light is a high-energy packet. A photon of red light is a low-energy packet. To escape from the metal, an electron needs a certain minimum amount of energy, called the work function. If a low-frequency red photon hits an electron, it doesn't have enough energy to free it. It doesn't matter if a billion of these weak packets arrive. None of them can do the job alone. This is the threshold frequency. But if a single high-frequency blue photon arrives, even from a very dim beam, it has enough power to instantly knock the electron free. The mystery was explained. Finally, the problem of instantaneous emission. The wave theory predicted a time delay for energy to build up. But in Einstein's picture, the process is not a slow absorption. It's a collision, a discrete event. A photon transfers its entire packet of energy in a single instant. If that energy is enough, the electron is ejected immediately. There is no waiting. The third mystery vanished. Einstein's idea was so different from the century of evidence for the wave nature of light that it was met with skepticism. The prominent experimental physicist Robert Millikan was unconvinced and spent 10 years conducting precise experiments designed to disprove Einstein's theory. But the more he measured, the more his data perfectly matched Einstein's predictions. In a demonstration of scientific integrity, Millikan had to conclude that his own work provided clear verification of Einstein's idea. His experiments, intended to destroy the concept, became its most powerful confirmation. For this work, Millikan was awarded the Nobel Prize in Physics in 1923. 2 years earlier, in 1921, Albert Einstein had been awarded his Nobel Prize, not for relativity, but for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. The light quantum was real. A new kind of reality, the implications. The confirmation of Einstein's idea did more than solve a puzzle. It revealed a new reality, a world far stranger than anyone had imagined, the quantum world. The implications of this discovery were profound, and they continue to shape our understanding of the universe. The most important implication is the concept of wave-particle duality. For over a century, the question had been, is light a wave, or is it a particle? Young's experiment showed it behaves like a wave. Einstein's explanation, confirmed by Millikan, showed it interacts like a particle. The conclusion was that both were true. Light is not either a wave or a particle. It is somehow, paradoxically, both. This is a central idea of quantum mechanics. Light seems to show a different face depending on how we observe it. When it travels through space, it acts like a wave, spreading out and creating interference patterns. But when it interacts with matter, it delivers its energy at a single point, like a particle. The very act of measurement seems to influence the nature it reveals. This strange duality was not limited to light. In 1924, the French physicist Louis de Broglie proposed that if waves, light, can behave like particles, perhaps particles, like electrons, can behave like waves. A few years later, experiments confirmed it. Electrons fired at a crystal produced an interference pattern, the signature of a wave. Everything in the universe, it seems, has this dual nature. The classical distinction between matter and energy had dissolved. Reality was made of something more fundamental, quantum entities that were both. Another idea that changed was that of a deterministic universe. In classical physics, if you knew all the forces on an object, you could predict its future with certainty. The quantum world, however, is fundamentally probabilistic. You cannot predict exactly where a single photon will land. You can only calculate the probability of it landing in a certain area. This shift from certainty to probability was a deep change in thinking that troubled many physicists, including Einstein himself. But the legacy of Einstein's idea is not just abstract. It is woven into the fabric of our modern world. The photoelectric effect is a working principle you use every day. The most direct application is the solar panel. A solar panel is a device engineered to use the photoelectric effect. When sunlight, a stream of photons, hits the material in the panel, the photons knock electrons loose. The panel is designed to guide these freed electrons into a circuit, creating an electric current. Every solar-powered device is a quiet witness to Einstein's photons at work. The camera in your phone is another example. At its heart is an image sensor, a grid with millions of tiny light-detecting pixels. Each pixel is a microscopic photoelectric device. When you take a picture, the lens focuses light onto this grid, and each pixel simply counts the number of photons that hit it. A bright area in the scene sends many photons, generating a strong electrical signal. A dark area sends few. The camera then turns this map of signals into a digital image. Every photo you take is a quantum measurement. The list goes on. Automatic doors often use a beam of light hitting a photodetector. Light meters, barcode scanners, and smoke detectors rely on this fundamental principle. From our deepest theories of reality to the practical devices in our hands, the impact of that 1905 paper is immeasurable. Einstein's light trick was a key that unlocked a hidden layer of reality, forcing us to accept a universe that is dual, probabilistic, and fundamentally quantum. Conclusion. So, we have traveled from a world of perfect, predictable waves to a quiet puzzle that did not fit. We saw how the simple act of shining light on metal presented a contradiction that no one could solve. And then, we witnessed a young patent clerk, with one different idea, change everything. The idea that light is not a continuous flow, but a stream of tiny energy packets called photons. An idea that not only explained the photoelectric effect but also opened the door to the quantum revolution. The light that illuminates our world is more complex and mysterious than it appears. It is a constant, quiet dance between two different natures. It is a wave that spreads through space, and it is a particle that arrives in a single, instant collision. What Einstein revealed is that our everyday experience is the surface of a much deeper and more fascinating reality. The next time you step into sunlight, take a picture with your phone, or see a solar panel on a roof, take a moment to remember. You are not just being bathed in a gentle wave of energy. You are being touched by countless trillions of tiny, individual packets of light, each one carrying a secret that took the mind of Albert Einstein to unlock. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And it does get stranger. What happens when you try to watch which path a single particle takes in the double-slit experiment? The universe, it seems, knows you are looking. We will explore that quiet mystery in a future video. How light decides when to act like matter explained slowly. Everything you see, the light from your screen, the gentle sunlight from a window, carries a quiet secret. For most of its journey, it travels like a wave, spreading out as a field of possibility, a subtle disturbance passing unseen through the universe. But under certain conditions, it is asked to show its other nature. It must let go of its wave-like form and arrive at a single, precise point with the tangible impact of matter. It is a change as quiet and profound as a ripple on a pond suddenly becoming a single grain of sand. So, what is the exact condition? What is the quiet trigger that compels light to stop being a wave and behave like a particle? The answer is perhaps stranger than the question, and it reveals a fundamental rule about the nature of reality itself. It is a rule that scientists considered for centuries, a paradox that took generations of thought to unfold, and it all comes down to a single, simple action: the act of measurement. Today, we will walk, step by step, through one of the most deep and tranquil stories in all of science. We will move slowly, carefully, to understand the mystery of how and why light makes this monumental shift. This is not just a story about physics. It is about the strange and deep connection between interaction and reality. A quiet disagreement. For much of human history, the question, "What is light?" was a quiet disagreement. On one side were those who believed light was a stream of tiny, distinct particles. This was the corpuscular theory, and its most well-known advocate was Sir Isaac Newton. In his view, a beam of light was like a stream of unimaginably small, fast-moving pellets. This made a kind of intuitive sense. After all, the world we can touch is made of particles. A grain of sand is a particle. You cannot place 2 grains of sand in the exact same spot at the exact same time. If you throw a handful of sand at a wall, each grain hits one specific spot. If you throw them through an open doorway, they fly straight and create a pattern on the back wall shaped like the doorway. It was a simple, logical, and mechanical idea. Newton's theory explained reflection well. Light particles simply bounced from a mirror like a ball from the floor. It was a tidy universe. But on the other side of the disagreement was a completely different idea, supported by figures like Christian Huygens. They argued that light was not a particle. It was a wave. Think of ripples spreading across a pond. A wave is not a single object in one location. It is a disturbance, a vibration that travels through something else. And the most important quality of waves is what they do when they meet. Imagine 2 pebbles dropped into a still pond, a small distance apart. Each creates its own set of circular ripples. As these ripples expand, they meet each other. Where the peak of one wave meets the peak of another, they combine to make a larger peak. This is called constructive interference. But where the peak of one wave meets the trough, or low point, of another, they cancel each other out, and the water becomes still. This is called destructive interference. This behavior, interference, is the unique signature of a wave. Particles do not do this. If you fire 2 streams of sand at a target, the grains do not cancel each other in midair to create blank spots. They simply add up. For more than a century, these 2 ideas existed together. Newton's particle theory was more widely accepted, in large part because of his reputation. But the wave theory had a quiet piece of evidence waiting, an experiment so simple, yet so deep, that it would appear to settle the question. It would become one of the most important experiments in physics, one that contains what has been called the central mystery of the entire field. It is called the double-slit experiment. The unmistakable evidence for waves. To understand how this single experiment changed our view of light, let's build it slowly, using things from our everyday world. First, imagine a wall with 2 thin, parallel slits cut into it. Behind this wall is a second wall, which will act as a screen to record what happens. Now, let's imagine we have a machine that fires small particles, like grains of sand, toward the 2 slits. What pattern would we expect to see on the back wall? It seems like common sense. Some grains will hit the first wall and stop. Some will pass through the left slit and hit the back wall, creating a stripe. Others will go through the right slit, creating a second stripe. If we do this for long enough, we will see 2 distinct vertical bands on the back wall, a direct shadow of the 2 slits. This is the classic pattern for particles. There is no ambiguity. Each grain of sand follows a single, definite path. Now, let's change the experiment. Let's replace the sand machine with something that creates waves in a tank of water. The wall with 2 slits is now a barrier in the water. We start generating waves that travel toward this barrier. When the wave reaches the barrier, it passes through both slits at the same time. As the wave emerges on the other side, each slit acts like a new source of waves, creating its own semicircular ripples, just like our 2 pebbles in the pond. These 2 new sets of waves spread out and, importantly, interfere with each other. Where crests meet crests, you get large waves. Where crests meet troughs, the water stays flat. If we place our backstop wall in the water, what pattern will we see? We will not see 2 simple bands. Instead, we'll see a series of many bands. There will be a strong central band right in the middle, where the waves from both slits traveled the same distance and arrived together, reinforcing each other. On either side will be dark bands, areas of stillness where the waves have cancelled each other out. Then another bright band, then another dark one, fading as you move away from the center. This striped pattern is the asterisk interference pattern. It is the undeniable fingerprint of a wave. It can only be created if whatever is passing through the slits goes through both at once and interferes with itself. The stage is now set. Particles produce two bands. Waves produce an interference pattern. The outcomes are different and mutually exclusive. In 1801, a British scientist named Thomas Young performed this exact experiment using light. He shone a beam of light onto a barrier with two very small slits and observed the pattern on a screen behind it. What he saw was not two simple lines of light. He saw a clear, unmistakable interference pattern, a series of bright and dark fringes. The conclusion seemed inescapable. Light must be a wave. The disagreement appeared to be over. For the next 100 years, the scientific world rested on this seemingly solid truth. Light was an electromagnetic wave. Or so it seemed, because another, more stubborn mystery was quietly waiting. An observation that made no sense if light was only a wave. This phenomenon was so strange it would eventually contribute to a Nobel Prize for Albert Einstein and reopen the quiet disagreement all over again. It is called the photoelectric effect. And this is where light begins to show its particle side. The particle reappears. The photoelectric effect is what happens when light shines on a piece of metal and knocks electrons out of it. It was first noticed by Heinrich Hertz in 1887. He saw that when ultraviolet light hit a metal surface, sparks could jump more easily across a gap. But the details of this effect were deeply puzzling and contradicted the accepted wave theory of light. Let's set up the experiment. We have a piece of metal. We have a light source that we can control, changing both its brightness, intensity, and its color, frequency. And we have a detector that can tell us if electrons are being ejected from the metal, and how much energy they have. Here is what the wave theory of light would predict. First, the brightness of the light should determine the energy of the electrons. A brighter light is a more powerful wave, so it should eject electrons with more energy, making them move faster. The color of the light should not be the important factor. Second, if the light is very dim, there should be a delay. A weak wave would need time to transfer enough energy to an electron to allow it to break free from the metal. These predictions are logical, and they are completely wrong. Here are the experimental results that no one could explain. Result 1. The energy of the ejected electrons depends only on the color, frequency, of the light, not its brightness. If you shine a dim red light on the metal, nothing happens. Now, you make the light intensely bright. Still, nothing happens. The wave theory is already in trouble. That intense wave should be carrying a great deal of energy, but not a single electron is moved. Then, you switch to a very dim blue or ultraviolet light. Instantly, electrons begin to fly off the metal. If you make that blue light brighter, you do not get faster electrons. You just get more of them. The energy of each individual electron remains the same. Result 2. There is no time delay. The moment the right kind of light hits the metal, electrons are emitted, even if the light is incredibly faint. There is no build-up period. The energy transfer is instantaneous. This was a deep problem for classical physics. The results made no sense. It was like saying 1,000 gentle waves cannot move a single pebble on a beach, but one tiny, sharp raindrop can send a pebble flying instantly. The continuous, spread-out energy of a wave did not fit the facts. Then, in 1905, Albert Einstein offered a revolutionary idea. He looked at the work of Max Planck, who had suggested that energy could only be released in discrete packets, or quanta. Einstein took this idea a step further. He proposed that light itself is these packets. That light travels through space as a stream of tiny, discrete energy particles. These particles were later named asterisk photons. With this one idea, Einstein explained the photoelectric effect perfectly. Here is how his particle theory solves the puzzle. 1. Each photon carries a specific amount of energy, determined by its frequency or color. Einstein gave us the equation E equals h nu, where E is energy, nu is frequency, and h is a very small number called Planck's constant. A photon of blue light has a high energy. A photon of red light has a low energy. 2. When light shines on a metal, it is a bombardment of these photons. Each photon interacts with a single electron in an all-or-nothing event. The photon's entire energy is transferred to that one electron instantly. 3. The electrons in the metal need a minimum amount of energy to escape. This is called the work function. Now everything fits. The red light, no matter how bright, is a stream of low-energy photons. None of them, on its own, has enough energy to free an electron. But a single photon of blue or UV light is a high-energy particle. When it hits an electron, it transfers more than enough energy to overcome the work function, and the electron is kicked out. It is a one-on-one, instantaneous interaction. And making the blue light brighter simply means you are sending more high-energy photons per second. So, you knock out more electrons, but the maximum energy of each electron does not change. This was the moment light was forced to reveal its particle nature. When light interacts with matter, when it transfers energy, it does so not as a spread-out wave, but in single, concentrated, particle-like packets. But this created a quiet paradox. Young's double-slit experiment seemed to prove that light was a wave. The photoelectric effect seemed to prove that it was a particle. How can it be both? How can something be a continuous, spread-out wave and a tiny, localized particle? This is the central mystery. Light was living a double life. The only remaining question was, how does it seem to decide which nature to show? The answer would come from combining these two experiments into one final, quiet test. How light seems to decide. We are now at the heart of the mystery. We have two truths, both supported by careful experiment. When light travels, it behaves like a wave. When light interacts, it behaves like a particle. So, what happens if we force light to reveal its particle nature while it is traveling? This is where we return to the double-slit experiment, but with a quiet, modern update. Instead of a bright beam of light, we turn the intensity down so low that we are firing only one single photon at a time. A few seconds pass. Another photon is fired. Our backstop is now a sensitive screen that can record a small dot wherever a single photon lands. If light is a particle, then each photon we fire should go through either the left slit or the right slit, like a grain of sand. After firing thousands of photons, one by one, we should end up with the same pattern as the sand, two distinct bands of dots. But that is not what happens. When we fire the first photon, a single dot appears. Its location seems random. We fire another. A second dot appears somewhere else. At first, the dots look like they are landing without a pattern. But as we continue to fire thousands of photons, one at a time, a strange and beautiful order begins to emerge from the randomness. Slowly, dot by dot, the interference pattern builds up. The very same series of bright and dark bands from Thomas Young's wave experiment materializes. The photons are fired one at a time. There is no possibility of one photon interfering with another. And yet, the final pattern can only be created by interference. This means that each individual photon, traveling by itself, somehow goes through both slits at once, interferes with itself, and then lands on the screen at a position determined by that self-interference. It is as if the single photon leaves the gun, becomes a wave of possibility, explores both paths, and then, upon interacting with the screen, reappears as a single particle at a specific point. The wave nature governs its journey. The particle nature governs its arrival. The bright bands are simply the areas where the probability of landing was high. The dark bands are where the probability was zero. But this is where we ask the final question. This is where we find the trigger. We know the photon is somehow passing through both slits. What if we try to know which path it took? What if we place a tiny detector at one of the slits, say, the right slit, that can tell us a photon just went through here? This detector is our observer. It is a form of measurement. It does not block the photon, it just registers its passage. So, we begin the experiment again. We have our single photon gun, our two slits, our screen, and now, a detector at the right slit. We fire the first photon. The detector at the right slit registers it. A dot appears on the back screen. We now know that this photon went through the right slit. We fire another. This time, the detector is silent. The photon must have gone through the unobserved left slit. A dot appears on the screen. We continue this thousands of times, noting which path each photon took. Now, we look at the pattern that has formed. And the interference pattern is gone. Completely. In its place are two distinct bands of dots, exactly like the pattern we got with the grains of sand. The moment we observed which slit the photon went through, the moment we acquired that which path information, the photon stopped behaving like a wave. It was asked to choose a single path. By behaving like a particle at the slit, it continued to behave like a particle all the way to the screen, and the wave-like interference was lost. This is the trigger. The act of measurement, of interaction that provides information, is what asks light to let go of its wave nature and behave like matter. It becomes even more clear. What if we leave the detector in place but do not record any information from it? What if the path remains unknown? The interference pattern returns. The mere physical presence of the detector is not what matters. It is the act of it acquiring information, the measurement itself, that collapses the wave of possibilities into a single concrete reality. Light does not decide in a conscious way. Its fundamental nature, when traveling unobserved, is to be a wave of probability, a superposition of all possible paths. The condition that forces it to act like a particle is asterisk interaction. An interaction with a screen, an interaction with an electron, or an interaction with a detector. Any interaction that reveals its location causes the wave to resolve, and the particle nature emerges. When we are not looking, in the quantum sense, it is a wave. When we look, it becomes a particle. And looking simply means interacting with it. Conclusion: the new reality. So, we have journeyed from the quiet disagreements of Newton and Huygens to the strange wonderland revealed by modern experiments. We've discovered that light is not strictly a wave or a particle. It is both, and it is neither. A better description is that it is a quantum object that shows properties of both, depending on how you interact with it. When it moves freely, its behavior is best described by the mathematics of waves. But when it is asked to interact, to be emitted, to be absorbed, to be measured, its behavior is best described as a particle, a photon, delivering its energy in one discrete packet. This is not a decision made by light. It is a fundamental rule of the universe. The wave is the cloud of all possibilities, and the particle is the single reality that emerges when that cloud is asked to interact with the world. And this is not just an abstract idea. This wave-particle duality is the foundation of the technology around us. The particle nature of light is the principle behind solar panels and the digital sensors in our cameras. Each pixel is a tiny device, counting the photons that arrive. The wave nature of light is fundamental to how we understand things like lasers and radio communication. The story of light's double life reveals a universe that is far stranger and more subtle than our everyday senses can show us. It is a world where things do not have definite properties until they are measured, where a single particle can explore multiple places at once, and where the act of observation is an active participation in reality. Light does not just illuminate our world, it reveals the quiet and beautiful rules that govern it. The next time you see a sunbeam, you are not just seeing a wave or a stream of particles. You are seeing a quantum mystery, constantly unfolding, becoming matter only at the final moment when it arrives. The invisible rule that forces light's choice. There is a quiet rule woven into the fabric of the universe. It is not a law of motion or gravity, but something more fundamental. It governs light itself, and in turn, shapes the very nature of reality. For centuries, we thought we understood light, debating whether it was a particle or wave. The truth, when it was finally glimpsed, was something far more strange and unfamiliar than anyone had imagined. The world we see, the solid and predictable world, is not the whole story. Beneath it lies a place where the rules of our intuition no longer apply. It is a world where a single particle can be in many places at once, and where the simple act of looking at something changes what it is. This is the quantum world. At the heart of this world is light. For a time, it seemed to want to be everything at once, a ghostly wave spreading through space, exploring every possible path. But it cannot. An invisible rule prevents it. The moment we ask, "Where are you?" the world of possibilities recedes, and light is forced to become a single thing in a single place. It chooses. Today, we will take a quiet journey into this mystery. We will follow the subtle clues left behind by science and uncover the rule that guides the choice of light. It is a journey that may ask you to set aside what you think you know about reality. Because it suggests the universe doesn't just exist for us to see. In a very real way, the universe becomes what it is because we see it. A quiet debate. Before we can understand the unfamiliar world of quantum mechanics, we must first appreciate the world it replaced. For a long time, the nature of light was one of the great, quiet debates in science. The question was simple, but the answer was not, is light a particle, or is it a wave? On one side was Sir Isaac Newton. In the 17th century, he suggested that light was a stream of incredibly small particles, which he called corpuscles. This idea felt intuitive. Light travels in straight lines. It casts sharp shadows. If two beams of light cross, they pass through one another without disturbance, just as two streams of particles would. For Newton, light was made of things. On the other side of the debate was the Dutch scientist Christiaan Huygens. He argued for a different picture entirely. Light, he believed, was not a particle but a wave, moving through space like ripples on a pond. Each point on a wave front gives rise to new wavelets, which spread out and combine to form the next wave. This idea elegantly explained things that the particle theory struggled with, like diffraction, the subtle way light bends when it passes the edge of an object. If light were only particles, it should cast a perfectly sharp shadow. But it does not. The edges are soft and fuzzy, a characteristic of waves. We can see this with sound, which is also a wave. You can hear someone speaking from around a corner because the sound waves bend to reach your ear. Huygens argued light does the same thing, just on a much smaller scale. For more than a century, Newton's immense reputation meant his particle theory was favored. It was the common sense view. Particles are discrete. They exist in one place at a time. This is the classical world we know. Waves are different. They are spread out disturbances, patterns of energy that exist over an area, not at a single point. The debate seemed to lean toward particles. But in the early 19th century, an English scientist named Thomas Young performed an experiment. It was simple, elegant, and its results would offer a different picture, seemingly settling the debate for good. It revealed a behavior so unfamiliar, it would become the gateway to the quantum world. It is known as the double-slit experiment, and it is where our quiet investigation begins. The first clue. Imagine a wall with two thin, parallel slits in it. If you were to fire small particles, like grains of sand, at this wall, the result would be predictable. On a screen behind the wall, you would find two piles of sand, each one lined up with one of the slits. This is simple particle behavior. Each grain of sand passes through either the left slit or the right slit, and lands accordingly. Now, imagine the same setup in a shallow tub of water. If we create waves that travel toward the slits, something different happens. As the wave passes through, each slit becomes a new source of circular waves. These two new sets of waves spread out and interfere with each other. Where the peak of one wave meets the peak of another, they reinforce each other. Where a peak meets a trough, they cancel out. The pattern this creates on a back wall is not two simple bands. Instead, you see many bands. A bright one in the center, then dark ones, then more bright ones. This is called an interference pattern, and it is the undeniable signature of a wave. In 1801, Thomas Young performed this experiment with light. On the screen behind the two slits, he did not see two bright lines, as Newton's particle theory would suggest. Instead, he saw a pattern of bright and dark fringes. An interference pattern. The conclusion seemed inescapable. Light was a wave. For the next 100 years, this was the accepted truth. It seemed Huygens had been right. Physicists developed a complete theory of electromagnetism, where light was understood as an electromagnetic wave. The mystery appeared to be solved. Light was a wave, spreading through space and interfering with itself. But science is a slow and patient process. Just when a story seems complete, a new detail can emerge that doesn't quite fit. At the turn of the 20th century, a strange observation called the photoelectric effect could not be explained by the wave theory. It would reopen the case, thanks to a young patent clerk named Albert Einstein. The first clue had been found, but it was leading somewhere no one expected. A quiet contradiction. The story of the photoelectric effect starts with a simple observation. When light shines on a piece of metal, it can knock electrons from the surface. The wave theory of light made a clear prediction about how this should work. A brighter light, being a more intense wave, should knock out electrons with more energy. A dim light should knock them out with less energy, and might require some time to build up enough energy to dislodge one at all. But experiments showed something different. It was found that red light, no matter how bright, could not eject a single electron. Yet blue light, even if it was very dim, knocked electrons out instantly. And making the blue light brighter did not make the electrons faster, it just produced more of them. The speed of the ejected electrons seemed to depend only on the color of the light, not its brightness. This was a quiet, deep puzzle for the wave theory. It was like saying a gentle breeze can knock down a tree, but a hurricane cannot. It did not make sense within the established framework. In 1905, Albert Einstein proposed a solution. He asked, what if Newton's old idea was not entirely wrong? What if light was not a continuous wave, but was instead made of discrete packets of energy? He called these packets quanta, and we now call them photons. In Einstein's picture, the energy of each photon was determined by its color. Blue light photons had high energy, red light photons had low energy. The brightness of the light simply corresponded to the asterisk number of photons. Suddenly, the photoelectric effect made sense. A beam of red light, no matter how bright, is a flood of low-energy photons, none of which has enough energy on its own to dislodge an electron. A beam of blue light, however, is a stream of high-energy photons. Even a dim blue light contains photons that can each instantly transfer enough energy to an electron to set it free. A brighter blue light just means more of these photons, so more electrons are released. Einstein's idea was revolutionary, and it eventually earned him the Nobel Prize. It also created a profound challenge for physics. Young's experiment had shown clearly that light behaved as a wave. Einstein's explanation showed just as clearly that it behaved as a particle. It was a quiet contradiction. How could light be a spread out, continuous wave in one moment, and a localized, discrete particle in the next? This was not a minor detail. It became known as wave-particle duality, and it suggested that reality at its most fundamental level was far stranger than we had understood. The clues were pointing in opposite directions. To move forward, a new kind of experiment was needed, one that could probe this duality directly. A deeper stillness. The contradiction was stark. The double-slit experiment showed a wave. The photoelectric effect showed a particle. So, which one was it? Physicists considered that perhaps the wave pattern was just an effect of many photons interacting with each other. What would happen, they wondered, if the double-slit experiment could be run with just one photon at a time? With modern technology, this became possible. An apparatus was built that could emit a single photon, let it travel through the slits, and record its arrival as a single dot on a screen. If the photon is a particle, it must pass through either the left slit or the right. It cannot pass through both. So, after sending many photons, one by one, we should expect to see two simple bands, just like with the sand grains. An interference pattern should be impossible, as a single particle has nothing to interfere with. The experiment was run. The first photon was sent. It made a single dot on the screen. A second photon was sent. It made another dot in a different place. After hundreds of photons, the dots appeared scattered and random. It looked just as one would expect from individual particle impacts. But as the experiment continued, and thousands upon thousands of dots accumulated, something extraordinary and quietly startling began to emerge. Dot by single dot, the interference pattern began to build. The photons, each sent alone, were landing only in the bright areas of the wave pattern, and avoiding the dark areas entirely. Let this sink in. Each photon traveled alone, and yet, the final pattern was undeniably the result of interference. This leads to a conclusion that sits uncomfortably with our intuition. The single photon, somehow, passed through both slits at the same time and interfered with itself. To describe this, physicists developed a new language. They proposed that an unobserved photon does not exist as a particle. Instead, it exists as a wave function, a wave of probability describing all the places it could be. This wave of potential travels, passes through both slits, and creates an interference pattern of probabilities. The bright bands are where the probability of finding the photon is high. The dark bands are where it is zero. When the wave interacts with the screen, it collapses, and the photon appears in a single place, chosen according to those probabilities. So, when unobserved, light is like a ghost. It is a wave of pure potential, exploring all paths at once. It is only in the final moment of interaction that this world of possibilities gives way to a single, concrete reality. This, however, raises a further question. What happens if we try to watch the photon during its journey? What if we place a detector at the slits to see which path it really takes? This is the question that leads us to the invisible rule itself. The role of observation. We are faced with an unfamiliar situation. A single photon, left alone, behaves like a wave. Our intuition tells us this cannot be the whole story. A particle must follow a single path. So, let's try to find out which one. We can modify the experiment by placing a detector at the slits. This detector is designed to do one simple thing: register which slit the photon passes through. We now have a way to gain what physicists call which path information. We turn on the apparatus and send the first photon. Our detector clicks, right slit. A definite answer. The photon continues and makes a dot on the screen. We send another. The detector clicks, left slit. Another dot appears. We repeat this thousands of times. Each time, we get an unambiguous answer. Each photon is behaving like a well-behaved particle, choosing one path. It would seem the mystery is solved. The photon really does go through only one slit. But then, we look at the final pattern on the screen. The interference pattern is gone. In its place are two simple bands of dots, exactly where we would expect them if we were firing particles. The moment we learned which path the photon took, its wave-like behavior vanished. This is the invisible rule. The very act of observing which path the photon takes forces it to have a single path. By measuring it, we collapse its wave of potential. It is important to be clear about what this means. It's not that the detector is clumsy and physically disturbs the photon. The effect persists even with the gentlest possible measurements. The observer does not need to be a conscious human. It can be any interaction with the environment, a machine, an atom, a stray particle, that records information about which path was taken. The mere existence of that information is enough to destroy the interference. So, this is the rule. A quantum system can exist in a superposition of many possibilities only as long as there is no record of which possibility occurred. The moment that information is created, the superposition collapses. Reality chooses a side. Light seems to want to be a wave of possibility, but the law of measurement requires it to be a particle of fact. The crucial act is not looking. It is knowing. This is already one of the most profound discoveries in science. But physicists decided to push this idea to its absolute limit. They asked a question that sounds like it bends time itself. What if we decide whether to look after the photon has already passed the slits? The unwritten story. We've established the rule. If you know the path, you get a particle. If you don't, you get a wave. The physicist John Archibald Wheeler proposed a thought experiment to test this rule in an unusual way. It is called the delayed choice experiment. The setup is a more advanced version of the double-slit experiment. A photon passes the slits. After it has passed, when its behavior as either a particle or a wave should already be a fact of the past, we make a choice. We can either insert detectors, using a system of beam splitters, to learn which path it took, or we can choose not to look. Our intuition says our future choice cannot possibly affect the photon's past behavior. But in the quantum world, intuition can be a poor guide. When this experiment was performed, the results were staggering. If the scientists chose to look, the photons were found to have behaved like particles. No interference. If they chose not to look, the photons were found to have behaved like waves, creating an interference pattern. It is as if our choice in the present determines the story of the photon's past. An even more complex version, the delayed choice quantum eraser, makes this even clearer. In this setup, a photon passes the slits and is then split into two entangled twins. One twin, the signal photon, goes to a main screen. The other, the idler photon, is sent on a long detour. The signal photon hits its screen and its position is recorded long before we do anything to its twin. At the end of the idler's long journey, we have a choice. We can measure it in a way that reveals which path its twin took, or we can measure it in a way that erases that information. The mind-bending result is this. When we look at the total pattern of all the signal photons on the screen, it is just a random scatter. But if we then use the information from the idler photons to sort the signal photons into two groups, one where we kept the path information, and one where we erased it, something remarkable is revealed. The group of photons where we kept the path information forms a particle pattern, two simple bands. The group where we erased the path information forms a perfect wave interference pattern. This does not mean information is sent back in time. The overall pattern is always random until we use the future information to sort it. But it tells us that the story of a photon, whether it was a particle or wave, is not a fixed fact until all its quantum interactions are complete. Reality is not written in stone. It is a story that is written, and sometimes recontextualized, up to the final moment of measurement. Conclusion. The participatory universe. So, where does this quiet journey leave us? We began with a simple question. Is light a wave or a particle? We found that the answer is yes. It is something else entirely, a quantum entity whose identity is not fixed. When left alone, light exists as a wave of possibilities, exploring every path at once. This appears to be its natural state. But this state is fragile. It exists only in the absence of information. The moment the universe gains a record of its definite state, The moment at which path measurement is made, an invisible rule is quietly enforced. The ocean of possibilities evaporates, leaving behind a single, concrete particle. Reality is required to choose. The double-slit experiment, in all its forms, shows us this. It reveals that reality is not something we passively observe. The act of measurement, of gaining information, is part of what makes the world concrete. The physicist John Wheeler called it a participatory universe. We are not just an audience watching a finished story. In a very quiet and fundamental way, our interaction with the universe is part of the story itself. Our choice to measure, to ask, "Where are you?" is what helps transform the ethereal potential of the quantum world into the classical world we experience. The rules are fixed, precise, and unwavering. But they describe a reality where the observer and the observed are not entirely separate. The next time you look at the stars, or see sunlight stream through a window, remember the quiet, strange journey that light has taken. It was not a simple trip from there to here. It was a journey across a landscape of possibility, a ghostly wave exploring every conceivable path, only to have that world of potential collapse into a single point of reality the moment it met your eye. In that instant, you did not just see the light. You participated in the ceaseless, gentle, and mysterious act of creating what is real. Science just proved looking at reality changes it. What if the universe has a secret? A rule about existence so strange, so counterintuitive, it sounds like it's straight out of science fiction. What if I told you that the universe knows when you're watching? That the very fabric of reality, the stuff that makes up you, me, and everything we see, literally changes its behavior the moment we decide to look. This isn't some philosophical riddle or a spiritual metaphor. This is a scientific truth, proven by one of the most mind-bending experiments ever designed. For almost a century, it was the subject of a huge debate between the two greatest minds in physics, a puzzle that seemed to challenge the very definition of real. But now, the verdict is in. Science has finally confirmed the weirdest secret of the cosmos, forcing us to rethink everything we thought we knew. This is the story of that discovery, a journey into the quantum world, where looking at reality irrevocably changes it. Hook, asterisk. Imagine a wall with two impossibly thin, parallel slits cut into it. Now, imagine you're firing tiny, solid marbles, one by one, at this wall. Most will bounce off, but some will pass through one slit, and some will pass through the other. If you put a screen behind the wall to see where they land, you'd expect to find two distinct bands of marks, a clear pattern matching the two openings. It's simple, it's intuitive, it's how our world is supposed to work. But what happens if we swap the marbles for light? For centuries, a debate raged about what light really is. Is it a stream of tiny particles, just like our marbles? Or is it something else entirely? This simple setup, just two slits in a wall, would not only answer that question but would eventually tear down our entire understanding of reality, revealing a truth so bizarre it would keep Albert Einstein up at night for decades. The world of common sense. Before we go down the rabbit hole, let's just appreciate the world we think we live in. It's a world governed by what scientists call classical mechanics. It's the physics of Isaac Newton, the physics of our everyday lives. A world of predictable causes and definite effects, right? If you throw a baseball, you can calculate its path. You know its position and its speed at every single moment. The ball doesn't exist in some ghostly state of maybe here, maybe there. It follows one, and only one, path. The moon orbits the Earth along a precise, knowable ellipse. It isn't in multiple places at once. It has a definite location, even when nobody's looking. The other big part of our classical world is waves. Think of ripples in a pond. Drop one pebble, and a circular wave spreads out. Drop two pebbles side by side, and you get two sets of waves. Where these waves meet, something cool happens. Where the crest of one wave meets the crest of another, they add up to create a bigger wave. That's constructive interference. But where a crest meets a trough, they cancel each other out, leaving the water flat. That's destructive interference. If you put a barrier with two openings in that pond and sent a single, wide wave toward it, the wave would pass through both openings at once. Two new waves would pop out the other side and interfere with each other, creating a complex pattern of high peaks and flat calms. This interference pattern is the undeniable signature of a wave. So, in the classical world, things were simple. You had particles, solid objects that are in one place at one time. And you had waves, spread out disturbances that can be in many places at once. And here was the rule. An object is either a particle, or it is a wave. It couldn't be both. This was the bedrock of physics. Until it wasn't. A glimmer of the bizarre, Young's experiment. Our story begins back in 1801, with an English genius named Thomas Young. At the time, the top theory, pushed by none other than Sir Isaac Newton, was that light was made of tiny particles he called corpuscles. It made sense. Light travels in straight lines. It casts sharp shadows. It really seemed to act like a stream of microscopic marbles. But Young wasn't convinced. He saw wave-like behavior in light and designed a brilliantly simple experiment to settle it, the very same one we just described. He shone a beam of light onto a barrier with two tiny slits and watched to see the pattern it made on a screen behind it. If Newton was right and light was just particles, the result was a no-brainer. Two bright bands of light, direct copies of the two slits. The exact same pattern our marbles made. But that's not what he saw. Instead, what appeared on the screen was a series of alternating bright and dark stripes. The center was the brightest, with dimmer bands spreading out on either side, separated by strips of total darkness. It was an interference pattern. The exact same kind you get when water waves overlap. The conclusion was unmissable. Light was a wave. The bright bands were where light waves from both slits were adding together, and the dark bands were where they were canceling out. For 100 years, this was considered definitive proof. Newton was wrong. Light was a wave, but the universe's story wasn't over. Not by a long shot. In fact, the real mystery was just getting started. The first quantum mystery, light as a particle. For a century, the wave theory of light was king. It explained pretty much everything. But as the 19th century turned into the 20th, new cracks started to show. One of the biggest was a strange phenomenon called the photoelectric effect. Physicists found that when you shine light on metal, it can knock electrons off the surface. According to wave theory, a dim light should take a while to build up enough energy to kick an electron out. And a more intense, powerful light wave should kick out more energetic electrons. But that isn't what happened. Experiments showed that electrons were ejected instantly, even with the faintest light, or not at all. And making the light more intense didn't give the electrons more energy, it just knocked more of them out. The energy of the electrons depended only on the light's color. Blue light kicked out more energetic electrons than red light. And below a certain color, no matter how bright the light was, not a single electron would budge. This made zero sense with the wave theory. Then in 1905, a young patent clerk named Albert Einstein came up with a wild idea that would eventually win him the Nobel Prize. He suggested that light isn't a continuous wave. Instead, light energy comes in little, indivisible packets. He called them quanta. Today, we call them photons. Einstein's idea explained the photoelectric effect perfectly. A single photon of light smacks into a single electron. If the photon has enough energy, based on its color, it instantly knocks the electron out. A brighter light is just more of these photon bullets, so it knocks out more electrons, but the energy of each hit stays the same. It was a particle theory, plain and simple. But this created an impossible situation. Thomas Young's experiment had proven light was a wave. Now, Einstein's theory had just proven it was a particle. How could it be both? How could a single thing be a spread-out wave and a tiny, localized particle at the same time? This paradox was the birth of one of the strangest ideas in all of science: wave-particle duality. The universe was not playing by the rules of common sense. And the double-slit experiment was about to get a whole lot weirder. The heart of the strangeness, one particle at a time. The paradox was baffling enough. Maybe, physicists thought, the photons in a light beam were just interacting with each other, and their collective behavior just happened to look like a wave. It was a common-sense idea. And thanks to new technology, it was an idea they could test. Scientists built light sources so sensitive they could fire one single photon at a time. This was the ultimate test. If the pattern was caused by photons interfering with each other, sending them through one by one should kill the effect. Each lonely photon would have nothing to interfere with. It would go through the left slit or the right slit, and over time, we should see what we always expected: two simple bands. So, they ran the experiment. The single photon emitter was turned on. Click. A single photon is fired. A tiny dot of light appears on the screen. Click. Another photon, another dot somewhere else. Click. And another. For hours, they collected the impacts of millions of individual photons, each one sent completely alone. At first, the dots looked random. But as more and more built up, a ghostly image started to emerge. And as the scientists watched, their classical intuition was shattered. Slowly but surely, the dots were forming an interference pattern. Let the sheer impossibility of this sink in. Each photon was sent alone. There was nothing for it to interfere with. And yet, the pattern that emerged is the undeniable sign of something going through both slits at once and interfering with itself. It's as if each individual photon passed through the left slit and the right slit at the very same time. This is the principle of quantum superposition. Before it's measured, a particle doesn't have a single location. It exists in a superposition of all its possible locations at once. Its position is a wave of probability. That wave flows toward the slits, passes through both, and the two new waves interfere with each other, creating spots where there's a high probability of finding the photon, a bright band, and spots where there's zero probability, a dark band. Only when the wave hits the screen does this cloud of possibilities collapse into one reality. The photon appears at a single point, but where it appears was determined by the ghostly interference of its own probability wave. The particle isn't a particle or wave. It's something our everyday language just doesn't have a word for. This bizarre reality left physicists with one burning question: what happens if we peek? The observer enters the stage. The results were so confounding, they pushed physicists to the edge. If a single particle is somehow going through both slits at once, then we should be able to catch it. What if we put a tiny detector right at one of the slits? Let's say, the right slit. This detector will just tell us, yep, the photon went through here, or, nope, it didn't. By doing this, we'll finally know the which way information. We'll have exposed the particle's secret path. So, they run the experiment again. The detector is placed at the right slit, ready to spy on the photons. Click. A photon is fired. The detector at the right slit beeps. We know it went right. A dot appears on the screen. Click. The detector is silent. We know that one went left. A dot appears. Click. A beep. It went right. Millions of times, the process is repeated. We know, with total certainty, which slit every single photon went through. Now, we look at the pattern they made on the screen. And the interference pattern is gone. It has completely vanished. In its place are two distinct, single bands. The exact pattern you'd get from marbles. The moment we looked, the moment we knew which path the photon took, its wave-like behavior disappeared. It snapped out of its ghostly superposition and acted like a simple, well-behaved particle. This is the core of the observer effect. The very act of measuring which path the particle takes forces it to choose a single path. Now, it's critical to understand what observation means here. It has nothing to do with consciousness. It's any interaction that reveals information about the particle. Placing the detector at the slit meant the photon had to interact with it, and that interaction is what destroyed the superposition. This was too much for Albert Einstein. He famously declared, "God does not play dice with the universe." He believed there had to be some deeper, hidden variables, telling the particles where to go. This weirdness wasn't real, he argued, it just meant our theory was incomplete. This sparked a legendary debate between Einstein and the Danish physicist Niels Bohr. Bohr argued that it's fundamentally impossible to know both the particle and wave properties of an object at the same time. He called it complementarity. You can set up an experiment to see the wave, and you'll see a wave. Or you can set up an experiment to see the particle, and you'll see a particle. But you can never see both at once. Einstein refused to accept this. He devised a clever thought experiment to find a loophole. Imagine, he proposed, that one of the slits isn't fixed, but is on a delicate spring, a recoiling slit. If a photon passes through, it will give the slit a tiny momentum kick. By measuring the slit's recoil, we could know the photon's path. But, and this was Einstein's genius move, we'd be measuring the asterisk slit, not the photon directly. The photon would continue on, undisturbed, and should still create an interference pattern. We'd get to have our cake and eat it too. Know the path and see the wave. But Bohr's comeback was brilliant. He argued that Einstein forgot something. The slit itself is a quantum object. To measure its recoil precisely enough, you'd have to know its initial position very precisely. But according to Heisenberg's uncertainty principle, the more you know a particle's position, the less you can know its momentum. Bohr showed that in the process of measuring the slit's recoil, the slit's own position would become just uncertain enough to smear out and destroy the interference pattern. You couldn't win. For decades, this was just a thought experiment. The technology to test it simply didn't exist. Einstein's challenge remained a monumental, what if, at the foundations of physics. Until now, the verdict of a century, vindicating Bohr. For nearly 100 years, the Einstein-Bohr debate was a legend. But what was once a thought experiment has finally become a real one. In a breathtakingly sophisticated experiment, scientists have finally built Einstein's recoiling slit. A team of physicists at MIT, led by Wolfgang Ketterle, took on the challenge. They knew a normal slit on a spring wouldn't work. They needed slits that were themselves quantum objects. Their solution was ingenious. They used ultra-cold atoms, arranged in a lattice by lasers, to act as the slits through which single photons would pass. When a photon scattered off one of these atoms, it would give the atom a tiny momentum kick, a recoil. By measuring that recoil, they could get the which way information Einstein wanted. Here's the genius part. They could control the fuzziness or uncertainty of the atom's location. By doing this, they could essentially tune how much they knew about the photon's path, sliding a knob from no information all the way to full information. The result was a beautiful, direct confirmation of Bohr's complementarity principle. When they had no way of knowing the atom's recoil, a clear, high-contrast interference pattern appeared. The photon was a pure wave. Then, they started to gather more and more information about the recoil, allowing them to know with increasing certainty which path the photon had taken. As they did, the interference pattern began to fade. The wave-like behavior was disappearing in direct proportion to how much particle-like information they were gathering. Finally, when they had unambiguous knowledge of the path, the interference pattern vanished completely. The photon behaved exactly like a particle. Bohr was right. Einstein's attempt to outsmart the universe failed, because the universe's commitment to uncertainty is absolute. The very act of creating a record of the path is what destroys the interference. And this rule holds for bigger things, too. Other teams, notably at the University of Vienna, have shown wave-like interference with massive molecules made of thousands of atoms. These are objects far more substantial than a photon, yet when shielded from their environment, they also spread out like waves and pass through multiple slits at once. The moment you try to figure out which slit one of these giant molecules went through, its wave nature vanishes. What does reality mean? So, what does this all mean? We've gone from a simple experiment with light to the frontiers of modern physics. And the conclusion, at every turn, is the same. The reality we experience is not a passive movie we just happen to watch. It's an interactive process. The unobserved quantum world is a realm of pure potential, an ocean of probability waves. A particle isn't here or there. It's just possible. But the moment that particle interacts with anything, a detector, a recoiling atom, even a stray air molecule, a record is made. Information is exchanged, and in that instant, the wave of possibility collapses into a single, concrete fact. The particle is here. Now, how you interpret this is still up for debate. The Copenhagen interpretation, favored by Bohr, says it's meaningless to even ask what the particle was doing before we measured it. The only reality is the measured reality. Other ideas, like the many worlds theory, suggest all possibilities are real, that every measurement causes the universe to split into parallel branches, one for each outcome. In one universe, the photon went left, in another, it went right. But regardless of which interpretation you prefer, the experimental results are undeniable. The properties of a particle, like its path, aren't fixed attributes it carries around. They are brought into existence by the very act of measurement. The act of measurement doesn't just reveal reality, it plays a role in defining it. Conclusion: from a simple observation about light over 200 years ago to the incredible experiments of today, the journey to understand the double-slit experiment has taken us to the very heart of reality itself. We've learned that the world of the very small operates on rules that defy our intuition. It's a world of superposition, uncertainty, and entanglement. Science has now shown, more clearly than ever, that the act of observation, of interaction, is not a passive event. It's a fundamental process that transforms the ghostly realm of quantum possibility into the concrete world we know. It's a conclusion that's both humbling and empowering. It tells us that we aren't just spectators of the cosmos but participants. Our interaction with the world is a fundamental part of what the world is. So, the next time you look up at the night sky, remember that the starlight traveling for millions of years to reach your eye was, until that very moment, a wave of pure possibility. And you, simply by looking, collapsed that wave into a single, definite point in space and time. What do you think this profound connection says about our place in the universe? Let me know your thoughts in the comments. And if you want to keep exploring the biggest questions in science, make sure you subscribe and turn on notifications. The universe's biggest lie about reality. You feel that the world around you exists whether you're looking at it or not. That a tree falling in a forest makes a sound, even if nothing is there to hear it. That the moon is still there, hanging in the quiet darkness, even when you close your eyes. For your entire life, you've known a simple story about reality. It's a story of solid things, of paths that can be predicted, and a universe that unfolds with the steady elegance of a clockwork mechanism. A reality that is objective, solid, and separate from you, the observer. And yet, that story, as comfortable as it is, begins to unravel when we look very closely. There is one famous, and surprisingly gentle, experiment that quietly dissolves that picture of reality. It shows that on a fundamental level, the universe is not what it seems. It reveals that the building blocks of our world are not just one thing or another, but exist in a ghostly state of all possibilities at once. And that the simple, quiet act of interaction fundamentally changes what is there to be seen. This is not philosophy. It is not science fiction. It is the bedrock of modern physics, A truth so strange and so counter to our intuition that the greatest minds in history have grappled with it. It has invited us to ask the most profound questions we can. What is reality? What is the nature of existence? And what is the role of interaction in shaping the universe we observe? Today, we journey to the very edge of understanding, to a place where our common sense falls away and the universe reveals one of its deepest secrets. We are going to explore the single experiment that takes apart our classical view of the world and replaces it with a reality that is probabilistic, strange, and woven together with the act of observation itself. This is the story of the double-slit experiment, a clockwork universe. Before we can appreciate the strangeness, we need to understand the world it replaced. For centuries, the story we told ourselves about reality was one of beautiful, elegant certainty. It was a story written primarily by Sir Isaac Newton in the 17th century. His laws of motion and gravity painted a picture of a clockwork universe. Imagine a cosmic billiard table, perfectly still. If you know the exact position and mass of every ball, and you know the exact force and angle of the strike, you could, in principle, predict the entire future of that table. You could know where every ball will go, which will collide, and where they will all come to rest. The entire game is determined from the very first moment. This was the vision of the universe that shaped scientific thought. From the orbit of a planet to an apple falling from a tree, everything was governed by precise, predictable laws. The universe was a grand machine. If you could know the state of every particle in it at one moment, its position and its momentum, you could theoretically calculate the entire future and the entire past of the cosmos. This idea was so powerful it led the French scholar Pierre-Simon Laplace to imagine a vast intellect that could know the location and motion of every atom. For such an intellect, he wrote, nothing would be uncertain in the future, just like the past, would be present to its eyes. This is the reality that feels natural. It's intuitive. Things are solid. They are in one place at one time. A ball thrown at a wall with two openings will go through one opening or the other. It can't go through both. Its path is definite. This is the world of particles. Let's hold on to that idea, because it's the perfect foundation for our experiment. Imagine we have a wall with two thin, parallel slits in it. And behind that wall, we have a screen that will record where things land. Now, imagine we have a machine that fires small particles, like grains of sand, one after another, at this wall. What pattern would you expect to see on the screen behind it? It's simple, isn't it? Some particles will be blocked. Others will happen to go through the left slit and make a mark. Still others will go through the right slit and make a mark there. If you run this for long enough, you'll end up with two distinct bands on the screen, each one a simple record of the particles that passed through one of the two slits. This is how particles behave. Each grain of sand is a separate object. It follows a single path. It goes through either slit 1 or slit 2. It cannot do both. The pattern is just the sum of these individual journeys. It's common sense. It's the classical world. It's the story we thought was true. Because when we shrink this experiment down to the fundamental pieces of our universe, things like electrons and light, something entirely different happens. Something our classical intuition is not equipped to explain. And it begins with a man who, over 200 years ago, decided to ask a simple question about the nature of light. A world of waves. For a long time, there was a great debate about what light actually is. Isaac Newton believed it was made of tiny particles, which he called corpuscles. But in 1801, an English polymath named Thomas Young conducted an experiment that seemed to settle the question. Young wasn't using particles of sand, he was using light. His setup was nearly identical. He shone a beam of light onto a barrier with two thin slits. If light were made of particles, as Newton thought, the result on the screen behind the slits should have been just like our grains of sand, two bright bands. But that is not what he saw. Instead of two bright bands, Young saw a series of many bright and dark bands, alternating across the screen. The center was the brightest, with dimmer bands spreading out to either side. This pattern was immediately familiar to physicists. It was an interference pattern. Interference is something that waves do, not classical particles. To understand this, let's turn to an analogy. Waves in a quiet pond. Imagine you dip two fingers into the water, side by side, creating two sources of spreading ripples. Where the waves from the two sources meet, something interesting happens. In some places, the crest of a wave from one source meets the crest of a wave from the other. They add together, creating a larger wave. This is called constructive interference. But in other places, the crest of a wave from one source meets the trough of a wave from the other. At these points, they cancel each other out, and the water stays calm. This is destructive interference. If you placed a back wall in the pond, you wouldn't see two splash marks. You'd see a pattern of high splashes and still water, reflecting this interference. This is exactly what Thomas Young saw with light. The bright bands were areas of constructive interference, where light waves passing through both slits arrived in sync. The dark bands were areas of destructive interference, where the waves arrived out of sync, canceling each other into darkness. The only way for this to happen is if the light, upon reaching the barrier, doesn't act like a particle going through one slit or the other. It must act like a wave that passes through both slits at the same time. The two new waves then spread out and interfere with each other before reaching the screen. Young's experiment seemed to prove definitively that light was a wave. For the next 100 years, this became the accepted truth. The work of James Clerk Maxwell in the 1860s solidified this, showing light was an electromagnetic wave. The case seemed closed. Reality was still a clockwork, but one of its pieces, light, was a continuous wave. But physics was about to enter the 20th century, and a new mystery was emerging. A quiet, stubborn observation that the elegant wave theory simply could not explain. Its solution would come from a young Albert Einstein, who would, in the process, reveal another layer of strangeness to the world. A spanner in the works, the particle returns. The problem that emerged was called the photoelectric effect. It's what happens when you shine light onto a piece of metal, and it knocks electrons loose. This effect is the basis for things like solar panels and digital cameras. According to the wave theory, a brighter light was a more energetic wave. So, a brighter light should knock out electrons with more energy. And even a very dim light, if you left it on long enough, should eventually give an electron enough energy to break free. But experiments showed something completely different. Something that didn't fit. It turned out that the energy of the freed electrons did not depend on the light's brightness at all. What mattered was the light's color asterisk, or frequency. A very bright red light might not dislodge any electrons, while a very faint blue light could dislodge them instantly. Below a certain frequency, no electrons were emitted, no matter how bright the light. Above that frequency, electrons were emitted immediately, and their energy only increased if you increased the light's frequency, moving from red toward blue, not its brightness. From a wave perspective, this made little sense. It would be like saying that no matter how many gentle ocean waves hit a coconut tree, the coconut will never fall. But a single, sharp, high-frequency ripple could knock it out instantly. In 1905, Albert Einstein proposed a revolutionary idea. He suggested we should revive Newton's old concept and think of light as being made of discrete packets of energy. He called these packets quanta of light. We now call them photons. Einstein theorized that a single photon's energy was tied only to its frequency. A photon of blue light simply has more energy than a photon of red light. The photoelectric effect, then, wasn't about an electron slowly absorbing a wave. It was a one-on-one interaction between a single photon and a single electron. If the photon has enough energy, the electron is knocked free instantly. If it doesn't matter how many photons you send. It's like trying to knock down a bowling pin by throwing ping-pong balls at it. Einstein's explanation was a monumental achievement, but it created a deep puzzle. Young's experiment proved light is a wave. Einstein's explanation proved light is a particle. How can it be both? A wave is spread out. A particle is in one place. Something cannot be both spread out and localized at the same time. And so, the stage was set for the ultimate experiment. Physicists decided to combine these two ideas. They would perform the double-slit experiment, but they would turn the light source down until it was so faint that only one single photon was sent at a time. This is where the comfortable story of our reality unravels completely. This is where the universe shows us just how strange it truly is. The ultimate experiment, reality unmade. Let's return to our experiment. A wall with two slits and a detector screen. But now, our light source is so weak that it releases only one photon at a time. A single, indivisible particle of light. What should we expect to see? If a photon is a particle, it must go through one slit or the other. It can't split. So, as we fire thousands of them, one by one, we should see them build up in two simple bands, just like the grains of sand. This would prove light is fundamentally a particle. So, the experiment begins. The first photon is fired. It makes a single dot of light on the screen. It landed in one specific place. Just like a particle. A second photon is fired. A second dot appears somewhere else. A third. A fourth. One by one, the photons make their individual marks. At first, the pattern is random. Just dots scattered on the screen. The particle model seems to be correct. But then, as thousands of these individual impacts accumulate, a ghostly, impossible pattern begins to emerge from the quiet randomness. It's the interference pattern, the very same series of many bright and dark bands that Thomas Young saw with a continuous wave. Let this settle for a moment. We are firing one particle at a time. Each photon travels alone. There are no other photons for it to interfere with. And yet, the final pattern is one that can only be created if something went through both slits at once and interfered with itself. It's as if each individual photon, when unobserved, ceases to be a particle. It spreads out like a wave of possibility, passes through both slits simultaneously, and the two resulting paths interfere with each other before it resolves back into a particle, landing at a single point on the screen. The final resting place of each photon is probabilistic. It is more likely to land where the interference is constructive, and will never land where it is destructive. This behavior, known as wave-particle duality, is a foundation of quantum mechanics. It seems that light, and in fact, all matter, is not simply a particle or a wave. It is something else, something for which we have no perfect word. But this is where it gets even stranger. The physicists, faced with this puzzle, decided to ask the obvious question. Which slit did it really go through? They decided to find out. They modified the experiment by placing a gentle detector next to one of the slits. This detector would simply register if a photon passed by, providing information about its path without blocking it. It is the simple act of gaining knowledge. So now, the experiment runs again. One photon at a time. The first photon is fired. The detector at the right slit registers its passage. It went through the right slit. A dot appears on the screen directly behind that slit. Another photon is fired. This time, the detector is silent. It must have gone through the unmonitored left slit. A dot appears on the screen behind the left slit. Another. The detector registers it. Right slit. Another. Silent. Left slit. One by one, we fire thousands of photons. Each time, our detector tells us which path the photon took. It behaved like a well-behaved particle, going through one slit or the other. Never both. And what pattern do we see on the screen after all the photons have landed? The interference pattern is gone. Completely vanished. In its place are two simple, distinct bands. The exact pattern we would expect from grains of sand. The very act of observing the photon's path, the act of gathering information about its journey, caused it to behave like a particle. When we did not know its path, it behaved like a wave passing through both slits. When we gained information about its path, it chose one. It seems the universe does not permit us to witness both its wave nature and its particle nature at the same time. Our interaction with the system, the question we choose to ask of it, determines the aspect of reality that is revealed. What does it all mean? The new reality. This result is so profoundly strange that physicists have spent a century quietly debating what it truly means. There is no single, agreed-upon answer. Instead, there are several interpretations, each a different attempt to build a coherent picture of reality from these experimental facts. Let's explore the two most famous ones. First, there is the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg. In many ways, this is the standard interpretation. It suggests that physical systems do not have definite properties, like a specific position, before they are measured. Instead, they exist in a superposition, a mixture of all possible states, described by a mathematical object called a wave function. In this view, the photon does not have a definite position. It is a wave of potential. The act of measurement or any interaction that extracts information causes this wave function to collapse, and the particle settles into one single, definite state. Before we look, the photon has the potential to go through both slits. When we interact with it to see which slit it used, that potential collapses, and it ends up going through only one. The Copenhagen interpretation suggests that the quantum world is fundamentally probabilistic, and that it is not meaningful to ask what a particle was really doing before it was measured. But this idea of a mysterious collapse caused by measurement didn't sit well with everyone. It seemed to create a strange dividing line between the quantum world and our everyday world. This led to a second, even more mind-bending idea, the many worlds interpretation. Proposed by Hugh Everett III, it makes a radical claim: the wave function never collapses. Instead, every time a quantum measurement could happen, the entire universe splits. All possible outcomes of the event actually happen, each in its own separate, parallel universe. When the unobserved photon hits the screen, the universe splits. In one universe, it lands at point A. In another, it lands at point B. When we place a detector at the slit, the universe splits then. In one universe, you see the detector register the photon. In another, a parallel version of you sees it remain silent. From your perspective within any one branch, it looks like a random collapse has occurred. You only ever experience one outcome. But according to this idea, all outcomes are equally real. The interference pattern disappears when we look because the you who saw the photon go left is now in a different universe from the you who saw it go right. There is no collapse, only an endless, quiet branching of realities. There are other interpretations. What they all agree on, however, is the fundamental lesson of the experiment. The clockwork universe of Isaac Newton is gone. The simple story of an objective reality that exists independently of us is no longer a complete picture. We began with a simple story: that the world is a collection of solid, definite objects, existing in a fixed state, waiting for us to perceive them. The double-slit experiment quietly dismantles that story. It shows us a world that is fundamentally uncertain, a world of shimmering probabilities and potentials. It tells us that the building blocks of everything, light, electrons, the atoms in our bodies, do not have a definite reality until revealed by interaction. Whether you believe that interaction forces a random collapse, or that it splits the universe into countless worlds, the conclusion is similar. The observer is not a passive bystander. The act of measurement, of gaining information, is part of how reality takes form. You are not separate from the universe you observe, you are a participant. This is not a comfortable idea. It does not fit our everyday experience. But for 100 years, every experiment has confirmed this strange truth. The quantum world is not just a smaller version of our world. It operates by different rules, rules that challenge our very definition of what it means for something to be. The world you see is not the world as it is. It is the world as it is observed. The next time you look at the moon, you can remember that on a fundamental level, the universe is not just presenting you with a pre-written story. It is responding to the questions that are asked of it, and the questions we choose to ask can determine the reality we find. The greatest mystery, perhaps, is not what lies out there in the darkness, but the profound, unbreakable link between the observer and the observed, between our awareness and the cosmos. If this quiet journey to the edge of reality helped you see the world a little differently, consider liking the video and subscribing to the channel. We explore the deep and often strange stories of our world every week. And we'd love to hear your thoughts in the comments below. Which idea feels closer to you? The single, unfolding reality of Copenhagen, or the endless branching realities of many worlds? Feel free to share. Thank you for listening. The impossible crystal that flows like water. Imagine, for a moment, cupping your hands to hold a beam of sunlight. It has no weight, no real substance, and it's impossible to truly hold. But what if, for just a moment, it wasn't? What if that warmth in your hand could suddenly settle, sparkle, and then arrange itself into a crystal you could feel, a solid structure with a definite shape? And then, what if that crystal, still glowing, slipped through your fingers, flowing like water? It sounds like something from a quiet story, a dream from the edges of science fiction. But in recent years, a team of physicists in Italy did something very close to this. They created a state of matter that feels like it shouldn't exist. A crystal made of light that can flow with zero friction. This is not an analogy. It is a new, and quietly bizarre, state of matter called a photonic supersolid. It is both perfectly ordered, like a diamond, and perfectly fluid, like a liquid that has no resistance to flow at all. This discovery does more than just bend the rules of physics. It seems to dissolve them, and then build something new from the pieces. For decades, the very idea was a contradiction. But now that it's real, it encourages us to ask a gentle, fundamental question. What does matter? And what else can light become? Here, we're going to explore how scientists managed to coax light into this impossible crystal, what it was like to chase this idea for over 50 years, and what this quiet breakthrough might mean for a future of quantum technologies we are only just beginning to imagine. The foundation, the rules of a broken game. To understand how profound a supersolid is, we first have to remember the quiet rules it appears to break. In our everyday world, the lines between the states of matter feel clear and absolute. First, there are solids. Think of a crystal of salt. At its smallest level, a crystal is a place of quiet order. Its atoms are locked into a rigid, repeating pattern called a lattice. Each atom has its place, and it does not leave it. It can vibrate with heat, a slight jiggling in its fixed position, but it cannot wander. This unmoving structure is what gives a solid its familiar properties, its hardness, its ability to hold a shape. It is the very definition of ordered matter. Then, there are liquids. Think of water. At the atomic level, a liquid is a state of controlled chaos. Its molecules are still packed closely together, but they have no fixed positions. They are free to tumble, slide, and jostle past one another. This is why a liquid can flow and take the shape of its container. A key property of any normal liquid is its viscosity. Viscosity is its internal friction, a measure of how much it resists flowing. Honey is thick and slow, with a high viscosity. Water flows easily, with a low viscosity. But every normal liquid has some resistance. Its molecules rub against each other as they move. For more than a century, these two states, the rigid, ordered solid and the disordered, flowing liquid, were seen as separate. A thing could be one or the other. It could not be both at once. The order of a solid prevents flow, and the flow of a liquid requires disorder. But the universe, at its smallest scales, does not always follow our familiar rules. When you get cold enough and small enough, you enter the world of quantum mechanics, and everything changes. Here, particles can behave as both particles and waves at the same time. And it is in this strange, quiet realm that the rules of solids and liquids begin to blur. This brings us to the first piece of our puzzle, the superfluid. In the 1930s, scientists discovered something extraordinary about the element helium. When you cool its most common form, helium-4, to just a few degrees above absolute zero, it transforms into a superfluid. This is a liquid that seems to defy logic. It has precisely zero viscosity and flows without any friction at all. If you were to stir a cup of superfluid helium, it would, in theory, continue to swirl forever. This strange behavior comes from a quantum phenomenon known as a Bose-Einstein condensate, or BEC. In this extreme cold, the individual helium atoms lose their identities. Their quantum wave functions overlap, and they begin to act as a single, massive, superatom, moving in perfect unison. This is what allows for the frictionless flow. The atoms move together as one, with no individual parts rubbing against each other. So now we have two extremes. The perfect crystal, a monument to order, and the perfect superfluid, a substance of absolute, frictionless flow. For a long time, they remained on opposite sides. But in 1969, two Soviet physicists, Alexander Andreev and Ilya Lifshitz, asked a quiet, revolutionary question. What if you could have both at the same time? They proposed a theory that was difficult to imagine. Think of a quantum crystal, like solid helium. Near absolute zero, atoms are so weakly held that they are constantly jiggling due to quantum fluctuations. Andreev and Lifshitz theorized that these jiggles could be so strong that they knock some atoms out of their lattice spots, creating empty spaces, or vacancies. And here is the brilliant idea. They proposed that these vacancies weren't just empty spaces. In the quantum world, they could act like particles themselves. If these vacancy particles could condense into their own Beck, they would form a superfluid asterisk of vacancies that could flow frictionlessly through the solid crystal. A flow of vacancies in one direction is the same as a flow of atoms in the opposite direction. The result would be a single substance that is simultaneously a perfect crystal and contains a part that flows without friction. It would be a super-solid. For nearly 50 years, this idea remained a theoretical dream, waiting for someone to make it real. The journey of discovery, chasing a ghost of light. The search for the super-solid became a long, quiet journey, marked by moments of hope and then, later, correction. The first and most obvious place to look was the one Andreev and Lifshitz had predicted, solid helium-4. In 2004, the physics world felt a stir of excitement from an announcement by a team at Pennsylvania State University, led by Moses Chan and his student Eun Seong Kim. They had designed an experiment using a device called a torsional oscillator, a small container of solid helium that they twisted back and forth. The principle was simple. The speed of the twisting depends on the mass inside. If all the helium was a normal, rigid solid, it would all twist together. But as they cooled the solid helium, they saw something unexpected. The twisting frequency suddenly increased. This suggested that the mass being twisted had decreased. It was as if a portion of the helium had separated itself and was no longer taking part in the rotation. The interpretation was stunning. This was the signature of a super-solid. A superfluid part had formed, and because it had zero friction, it remained still while the crystal twisted around it. Their paper cautiously called it the probable observation of a super-solid helium phase. The discovery created a wave of interest, and many labs tried to reproduce the results. But doubt remained. The effect was small and not always consistent. For 8 years, the community debated and retested. Then, in 2012, came a moment of remarkable scientific honesty. Moses Chan himself published a new paper that disproved his own discovery. A new experiment showed the effect wasn't from a super solid after all. Instead, it was caused by the solid helium simply becoming stiffer at low temperatures, a normal materials effect, not a new state of matter. The dream of a helium supersolid had been a false dawn. The community was disappointed, but the search was not over. It simply needed a new path. If a supersolid could not be found, perhaps it could be built. The new frontier was the world of ultra-cold atomic gases. These are clouds of atoms cooled by lasers to temperatures billions of times colder than outer space. At these temperatures, the atoms form a Bose-Einstein condensate, the same state that makes helium a superfluid. This BEC was a blank canvas on which physicists could try to create a supersolid. In 2017, the breakthrough finally came, not from one lab, but from two, at almost the same time. A team led by Wolfgang Ketterle at MIT and another by Tilman Esslinger at ETH Zurich both created the first definitive supersolids. They used different methods, but the core idea was the same. They started with a BEC, a perfect superfluid. Then, using carefully tuned laser beams, they encouraged the atoms to interact in a way that caused them to spontaneously arrange themselves into a regular, repeating pattern. They formed a crystal. But because this structure was made from the atoms of the BEC itself, the entire thing remained a superfluid. They had created a substance with a crystalline structure that could also flow without any friction. After nearly half a century, the supersolid was finally real. It wasn't found, it was engineered. This success opened a new, even more audacious question. Scientists had made a supersolid from atoms. But could it be done with light itself? This challenge seemed immense. Photons, the particles of light, are famously antisocial. Two beams of light can pass right through one another as if the other isn't there. To build a crystal from them would require a new kind of physics, a way to force photons to not only notice each other but to organize themselves into a structured state. The explanation: how to build an impossible crystal of light. The challenge of building with light came down to a single, fundamental problem. Photons do not naturally interact with each other. The solution, it turned out, was not to change the photons, but to give them a partner. This is where we meet the secret ingredient, a quiet hybrid particle called a polariton. A polariton is what is known as a quasi-particle. It is not a fundamental particle like an electron, but an entity that emerges from complex interactions inside a material. You can think of it as a particle that is half light and half matter. The experimental setup, developed by teams like the one at Italy's National Research Council, CNR, is a work of quiet precision. It begins with a quantum well, a microscopic sandwich of different semiconductor materials, such as gallium arsenide. Here is how a polariton is born. First, scientists fire a laser at this semiconductor sandwich. The laser's energy creates what is called an exciton, a bound pair of an electron and the hole it leaves behind. This exciton is the matter half of our hybrid. At the same time, the semiconductor layers are designed to act like two tiny, perfect mirrors that trap a photon of light, causing it to bounce back and forth. This trapped photon is the light half. When the conditions are just right, the trapped photon and the exciton couple together so strongly that they merge into a new entity, the polariton. This hybrid particle inherits traits from both its parents. From the photon, it gets its very small mass. From the exciton, the matter part, it gets the crucial ability to interact with other polaritons. Suddenly, light is no longer antisocial. It has been given a way to feel. With this tool, the Italian team could begin to build their crystal. The process is a delicate ballet of cooling and condensing. First, the system is cooled to temperatures approaching absolute zero. Next, they pump the system with enough laser light to create a dense gas of these polaritons. As the density increases, something remarkable happens. Just like helium atoms or ultracold atoms, the polaritons all collapse into a single, unified quantum state. They form a polariton condensate, which is a superfluid made of light and matter that flows with zero viscosity. But the team took it a step further. To get a supersolid, they engineered the surface of their semiconductor, etching a pattern of microscopic ridges onto it. Now, the magic happens. The polariton superfluid begins to interact with itself. The polaritons repel each other, and as they do this within the landscape of the ridges, they spontaneously self-organize. They settle into a regular, repeating pattern, forming dense clusters in the valleys. This is not a structure forced from the outside, it is a crystal lattice that the polaritons build themselves. They have formed a solid. And here is the quiet resolution to the paradox. The system has not become a solid instead of a superfluid. The crystal lattice is the superfluid. The density of the single quantum condensate is simply arranged into a crystal pattern. You can imagine it like a still lake that suddenly develops a perfectly regular, frozen wave pattern on its surface, even while the water underneath remains perfectly fluid. The entire structure can flow together without any friction because the underlying state is a single, coherent superfluid. To confirm they had truly created a photonic supersolid, the researchers performed careful tests. They used imaging to directly see the periodic pattern, the crystal lattice made of light. At the same time, they measured the properties of its flow and confirmed the entire structure could move without any resistance. It was a solid and a fluid, order and flow, all in a single quantum state made of light. So what? Why this crystal changes everything. The creation of a photonic supersolid is more than a laboratory curiosity. It quietly opens new fields of physics and technology by changing our relationship with light. For the first time, we have a way to make light behave like tangible matter. Perhaps the most immediate possibility lies in the world of quantum computing. For years, photons have been seen as ideal carriers of quantum information. They are fast and not easily disturbed. But they have a flaw: they are not good processors. Because they don't interact, it is hard to build logic gates, the basic building blocks of a computer, out of light. Photonic supersolids change this. By giving photons a way to interact, we can imagine creating all optical transistors and circuits that operate with light instead of electrons. Such devices could be vastly faster and more energy efficient than current electronics. Imagine a computer that processes information at the speed of light, with circuits that have no electrical resistance and generate almost no waste heat. This is the distant promise that solid light holds. Beyond specific uses, the photonic supersolid is a new kind of scientific playground. It is a quantum simulator, a controllable, artificial system that allows us to study some of the most profound phenomena in physics. Many body quantum systems, where countless particles all interact, are notoriously difficult to calculate. But photonic supersolids are potentially much easier to work with. They can be created and changed simply by shining lasers on a chip. Scientists can now watch quantum phase transitions happen in real time, simply by tweaking a laser. It is a new window into the fundamental laws of nature. And finally, this discovery brings a subtle shift in how we think about light. We are used to thinking of light as pure energy, something massless and separate from the world it illuminates. But the photonic supersolid blurs the line between light and matter. It shows that under the right quantum conditions, light can take on the properties of a tangible substance. It can have structure and a collective form. We are not just discovering the states of matter that nature provides. We are beginning, quietly, to invent our own. Conclusion: we began with a paradox. A crystal that flows, a solid that's also a liquid. We journeyed through a 50-year search that took us from a bold prediction, through the false dawn of the helium experiments, to the creation of atomic supersolids in 2017. And finally, we arrived at the laboratory where physicists coaxed ethereal light into a tangible, structured, yet perfectly fluid state, the photonic supersolid. They did it not with magic, but with the even more wondrous rules of quantum mechanics, using hybrid particles of light and matter to bridge the gap between two opposing states of being. This breakthrough isn't just a new entry in a textbook. It's a tool, a new lens through which we can explore the quantum world, and a potential cornerstone for future technologies like quantum computing and frictionless, light-based electronics. If this kind of calm exploration into the quantum world helps you unwind, consider liking the video and subscribing to the channel. We are living in an era where the fundamental rules of the universe are not just being read, but rewritten. We started with the idea of holding light in our hands. Now, scientists have essentially done just that, revealing that light isn't just something that illuminates our world. It's something with which we can build new ones. The supersolid was once a fantasy. Now it is a fact. It leaves us with a final, quiet question. What other impossibilities might become reality next? Feel free to share your thoughts in the comments below. The quantum switch that breaks reality. There is a quiet assumption we make about the world. That it exists, solid and predictable, whether we are watching it or not. A rock is a rock. A planet follows its orbit. For most of human history, this felt certain. The universe seemed to be a grand, cosmic machine, operating by consistent and knowable rules. But at the beginning of the 20th century, a series of discoveries revealed a quiet crack in that foundation. These discoveries suggested that at the smallest, most fundamental level, the universe behaves differently when it is unobserved. It suggested the simple act of looking at something could change its nature, forcing it to resolve from a haze of possibilities into a single fact. This is not a metaphor. It is the story of how our understanding of reality was slowly corrected. It is a quiet exploration into a strange set of rules the universe follows when it thinks no one is looking. This is the story of the quantum switch. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a quiet room, or somewhere in between, feel free to share where you're watching from. The clockwork universe. To understand how deeply our view of reality changed, we first need to appreciate the comfortable world we thought we lived in. For over 200 years, the universe made a kind of perfect sense. And the architect of that sense was Sir Isaac Newton. Before Newton, the cosmos was a place of mystery. But in the late 17th century, his laws of motion and gravitation provided a rulebook for the universe. Suddenly, the world was not so mysterious. It was a machine, intricate, but ultimately knowable. His laws described a world of cause and effect. If you knew the position and speed of a particle at one moment, you could, in principle, calculate its entire future. There was little room for ambiguity. Reality was set, and we were simply watching it unfold. In this clockwork universe, light also had its place. For a long time, its nature was debated. Newton believed it was a stream of tiny particles he called corpuscles. But in 1801, a man named Thomas Young performed an experiment that seemed to settle the question. It is an experiment central to our story, the double-slit experiment. Imagine a wall with two narrow slits in it. If you throw sand at it, you would expect to find two piles of sand on a screen behind the wall, one for each slit. Simple enough. But when Young shone a beam of light at the two slits, he saw something completely different. He did not see two bright lines. Instead, he saw a pattern of many bright and dark stripes. This is called an interference pattern, and it is something only waves do. Think of two pebbles dropped into a pond. As the ripples spread, they interfere with each other. Where two crests meet, the wave is amplified. Where a crest and a trough meet, they cancel out. This is what Young saw with light. The bright bands were where light waves added together. The dark bands were where they cancelled out. The conclusion seemed inescapable. Light was not a particle. Light was a wave. For the next century, this was accepted science. James Clerk Maxwell's equations on electromagnetism described light as a self-propagating wave, and the case seemed closed. The clockwork universe was complete and consistent. Light was a wave, matter was a particle, and the world was understood. Or so it seemed. Because beneath the surface of this classical world, a few quiet questions remained. A few small observations did not quite fit. And these quiet questions were about to unravel everything. The cracks in reality. At the end of the 19th century, there was a sense of confidence in physics. Some believed the fundamental laws of nature were known. Yet a couple of details refused to cooperate. They were like loose threads, and pulling on them would change everything. The first was a problem of heat and color, known as the black body radiation problem. A black body is an object that absorbs all light that hits it, and when heated, it glows. Think of iron in a forge. As it gets hotter, it glows red, then orange, then white. The color it emits changes with its temperature. Physicists tried to predict the spectrum of light a black body would radiate. Their theories, based on the classical idea of light as a wave, worked well for low-frequency light. But for higher frequencies, in the ultraviolet range, the theory failed completely. Classical physics predicted that a hot object should release an infinite amount of ultraviolet radiation. This was obviously not happening. If it were true, a simple lit match would be catastrophically dangerous. This failure became known as the ultraviolet catastrophe. It was a clear sign that the rules were incomplete. The solution arrived in 1900, from a German physicist named Max Planck. He tried something he did not fully believe. He proposed that energy might not be smooth and continuous. What if, he suggested, energy could only be emitted or absorbed in small, discrete packets? He called these packets quanta. With this new rule, an atom could not emit just any amount of energy. To produce high-frequency light, it had to generate a whole, high-energy packet, and at a certain temperature. Most atoms lacked the energy for this. This simple restriction solved the ultraviolet catastrophe. Planck's new equation perfectly matched the experimental data. But Planck himself was troubled by this. He considered it a mathematical convenience, not a description of reality. The idea that energy came in packets was foreign to classical physics, and he spent years trying to find another explanation. He could not. He had quietly uncovered the first piece of the quantum puzzle. It would take another mind to see Planck's mathematical trick as a fundamental truth. That mind belonged to a young patent clerk in Bern, Switzerland, Albert Einstein. He turned to a different puzzle, a phenomenon called the photoelectric effect. First observed in 1887, the effect is simple. When light shines on metal, it can knock electrons loose. Here was the mystery. According to wave theory, a brighter light carries more energy, so it should eject electrons with more force, making them move faster. But experiments showed something else. Whether electrons were ejected depended not on the light's brightness, but on its color asterisk, or frequency. A bright red light did nothing. But even a dim blue or ultraviolet light would eject electrons instantly. Furthermore, the energy of the ejected electrons also depended on the light's frequency. Higher frequency light produced faster electrons. A brighter light would eject more electrons, but not faster ones. This was inexplicable from a wave perspective. The world of classical physics had no answer. And in 1905, Albert Einstein offered a solution that would change science forever. Einstein's ghostly particles. Einstein looked at the black body problem and the photoelectric effect and saw a connection. Where Planck saw a quirk in how atoms emit energy, Einstein asked a different question. What if the packets were a property of the light itself? In one of his 1905 papers, Einstein proposed that light is not a continuous wave. Instead, he argued, it is a stream of discrete, particle-like packets of energy. The energy of each light quantum was proportional to its frequency, just as Planck had suggested. These packets would later be named photons. Suddenly, the photoelectric effect made sense. Think of the electrons as balls stuck in a ditch. A low-frequency red light is like a series of gentle taps. No single tap is strong enough to get a ball out. A high-frequency blue light is like a series of sharp kicks. Even a single kick has enough energy to send a ball flying out instantly. A brighter light means more photons, more kicks per second, so more balls are ejected. But the speed of any single ball depends only on the energy of the kick that freed it. Einstein's hypothesis explained the photoelectric effect with quiet elegance. For this work, for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect, he was awarded the Nobel Prize in Physics for 1921. But in solving one problem, he created a deeper one. The evidence was now split. Thomas Young's experiment from 1801 seemed to be undeniable proof that light was a wave. Einstein's explanation of the photoelectric effect was equally strong proof that light was a particle. So, what is it? A wave, or a particle? The two concepts seem to be opposites. A wave is a spread-out disturbance. A particle is a localized object. This was the birth of wave-particle duality, one of the central concepts of quantum mechanics. It set the stage for a modern version of Young's experiment, one that could ask the universe the question directly. The answer that came back was stranger than anyone expected. It was not one or the other. It was both. And it depends. It depends on whether you are looking. The ultimate experiment. The beauty of the double-slit experiment is its simplicity. By the 20th century, technology allowed physicists to perform it not with a beam of light, but with one single photon at a time. Imagine a device that fires one photon at a time toward the wall with two slits. Behind it, a screen records a small dot wherever a photon lands. First, let's close the right slit. We fire the photons one by one. Each one passes through the open left slit and makes a dot. Over time, a single band of dots builds up behind the open slit. This is what you would expect from particles. The same happens if we close the left slit and open the right one. A single band appears behind the right slit. So far, there is no mystery. Now, we open both slits and continue to fire the photons, one at a time. Common sense suggests what should happen. Each photon is a single particle. It must go through one slit or the other. Over time, we should see two bands of dots, a simple sum of the two previous results. But that is not what happens. The first photon lands, then the next, and the next. Each arrival is a single, distinct dot. But as thousands of these individual dots accumulate, a strange pattern emerges. We do not get two bands. We get the same striped interference pattern that Young saw with a continuous wave of light. This result is deeply strange. The photons are fired one at a time. There is only a single photon in the apparatus at any moment. And yet, the pattern that emerges can only be created if each photon somehow interfered with something. The only thing it could have interfered with is itself. But for a single photon to interfere with itself, it must have gone through both slits at the same time. A particle should not be able to do this. Only a wave can, spreading out and passing through both openings. So, the photon behaves in a way that is hard to picture. It seems to leave the source as a particle, spread out like a wave of possibility, pass through both slits, interfere with itself, and then register on the screen as a single particle again. The final position is random, but the probability of where it will land is described by that wave pattern. The logical next step is to try and see which slit the photon really goes through. We can place a detector near one of the slits, designed to simply note if a photon passes by. So we run the experiment again, with the detector turned on. The detector works perfectly. It confirms that each photon goes through only one slit or the other. It never goes through both. It is a particle, after all. But then we look at the screen. And the interference pattern is gone. In its place are just two simple bands. The very pattern we expected in the first place. This is the quantum switch. The moment we measure which path the photon takes, the moment that information is acquired, its wave-like behavior vanishes. It behaves like a simple particle. The ghostly wave of possibility collapses into a single, concrete reality because it was observed. It is as if the system's behavior depends on what is known about it. When the path is unknown, it explores all possibilities at once, like a wave. The instant the path is known, it settles into a single path, like a particle. This is not a disturbance in a classical sense. In more advanced experiments, the path information can be measured and then erased after the photon has passed the slits but before it hits the screen. When the information is erased, the interference pattern returns. The information itself seems to be the key. This shatters the classical view of an objective, independent reality. It suggests the universe does not have one set of rules, but two. One for when it is unobserved, and another for when it is. The act of measurement is not passive. It is an act of participation. If this quiet exploration into the nature of reality is something you find interesting, consider subscribing to the channel. We have just looked into one of the deepest mysteries of science, and now we must ask, what does it all mean? What does it all mean? The great debate. The double-slit experiment leaves us at a philosophical crossroads. The mathematics works perfectly. But what is a photon or an electron actually doing when we are not looking? This question led to one of the most important debates in the history of science, mainly between the physicists Niels Bohr and Albert Einstein. Niels Bohr was a primary architect of the Copenhagen interpretation, which for a long time was the standard view. Bohr argued that it is fundamentally meaningless to ask what a quantum system is doing when it is not being observed. Physics, in his view, is not about what reality is, but about what we can measure. According to this interpretation, before a measurement, a system like a photon does not have a definite position. It exists in a superposition, a mathematical combination of all its possible states at once. The wave that passes through both slits is a wave of probability. When a measurement happens, this wave of possibility is said to collapse. Out of all the potential outcomes, the universe randomly selects one. Before measurement, there is only probability. After measurement, there is fact. Albert Einstein found this idea difficult to accept. He believed the universe had to be objective, independent of our observations. His view was captured in his famous statement, "God does not play dice." He felt the randomness of quantum mechanics pointed to our own ignorance. There must be, he argued, some deeper reality, some hidden variables that we simply cannot see yet. For him, the photon really does go through one slit or the other. We just don't know which one. This led to decades of debate. Einstein would propose thought experiments to show that one could, in theory, measure a particle's properties without disturbing them. Bohr would, in turn, find the flaw in the reasoning, showing how the measurement would always alter the system in a fundamental way. For a long time, the debate seemed to be purely philosophical. Then, in the 1960s, a physicist named John Bell developed a theorem. Bell's theorem, and the experiments that followed, showed that Einstein's idea of local, hidden variables was incorrect. The correlations seen in quantum experiments cannot be explained by any theory where objects have definite properties before they are measured. The universe is genuinely stranger than Einstein was comfortable with. But the Copenhagen interpretation is not the only way to think about this. The idea of a collapse, caused by an observer, has always made some physicists uneasy. What counts as an observation? Does it require a person? A machine? This led to other ideas. The most famous is the many worlds interpretation, proposed by Hugh Everett III. Everett suggested that the wave function never collapses. Instead, every time a quantum measurement is made, the entire universe branches. When the photon reaches the slits, the universe divides. In one universe, it goes through the left slit. In a parallel universe, it goes through the right. In this view, you, the observer, also split. One version of you sees it go left, another sees it go right. You only experience one of these outcomes, but all of them are equally real. It is a staggering idea, but it is mathematically clean. It removes the need for a special collapse process. Conclusion: the unbroken reality. We began this journey in a comfortable, clockwork universe. By following the quiet, strange behavior of light, we have arrived in a place built on chance and ambiguity. We have found the quantum switch, a principle that suggests the properties of things at the smallest scales are not fixed until they are observed. An unobserved particle is a wave of pure potential. The act of measurement compels it to become a single, solid fact. This wave-particle duality applies to everything in the quantum realm: electrons, atoms, the building blocks of our own bodies. And while it may break our intuition, we have learned to use this strangeness. The technological world of the 21st century is built on quantum mechanics. Lasers, transistors, computers, and solar panels are all quantum devices. Future technologies like quantum computing seek to use these strange effects, like superposition, to accomplish things classical machines cannot. We live in a world built on a foundation we can barely comprehend. The solid, stable reality of our daily lives appears to be an illusion, an emergent property of a bubbling, uncertain quantum world beneath. We have pulled back the curtain and found that reality is far more subtle than we ever imagined. This leaves us with a quiet, lingering question. If the universe solidifies into a definite reality only when it is measured, what does that say about the nature of measurement itself? And what was the universe doing for the billions of years before any observer was here to see it? If a tree falls in a forest and no one is there to hear it, does it make a sound? Quantum mechanics pushes this question further. If nothing is looking, is the tree truly there? Or is it just a shimmering wave of possibilities, waiting for a glance to turn it into wood? What do you think is really going on when we're not looking? The 2026 discovery that bends the rules of existence. What if the solid ground beneath our feet isn't truly solid? What if the fabric of reality, the space and time we move through, has a hidden layer? A layer that isn't smooth, but granular, like a digital image zoomed in too far. For a century, this idea has quietly existed in the world of theoretical physics, a ghost in the mathematical machine. But what if we could finally see it? This isn't a story about a familiar particle or a distant galaxy. This is a journey into an idea, a discovery that could one day peer behind the curtain of the universe itself. An observation so profound it might force us to question the nature of existence. We're about to explore a hypothetical experiment, a breakthrough that could, for the first time, detect the influence of this hidden reality. This is the story of a discovery that could bend the rules of existence. Imagine you're in a dark room, holding a laser pointer aimed at a wall with two impossibly thin slits cut into it. The light behaves as you might expect, acting like a stream of tiny particles, creating two distinct lines on the wall. You are seeing light as a particle. But then, the experiment changes. The two lines dissolve. In their place, a complex pattern of light and dark stripes appears, like ripples overlapping in a pond. Suddenly, light is no longer a particle. It's a wave, passing through both slits at once and interfering with itself. This strange split personality is called wave-particle duality, and it isn't just a trick for light. It's the foundational mystery of quantum mechanics. And as it turns out, it's the secret key that might one day allow us to unlock a door we never knew was there. This quantum strangeness, this choice reality seems to make from moment to moment, is what could lead us to a glimpse of the universe's source code. The two pillars and the great abyss. To understand the monumental nature of what such a discovery would mean, we first need to appreciate a crisis that has defined modern physics for 100 years. It's a tale of two theories, two magnificent pillars of human thought that describe our universe with breathtaking accuracy, but are fundamentally incompatible with each other. On one side, we have Albert Einstein's general theory of relativity. Unveiled in 1915, it rewrote our understanding of gravity. Gravity, Einstein showed, is not some mysterious force. Instead, it is the consequence of mass and energy warping the fabric of spacetime. The classic analogy is a bowling ball on a stretched rubber sheet. The ball creates a curve, and a marble rolled nearby will be deflected by this curve, circling as if pulled by a force. That's gravity. General relativity is the physics of the large and the smooth. It governs the dance of planets, the swirl of galaxies, and the bending of starlight. Its predictions have been confirmed time and again, from the time corrections that make GPS work to the discovery of gravitational waves. Relativity paints a picture of the universe as a continuous, flowing, geometric masterpiece. On the other side of the abyss, we have quantum mechanics, the rulebook for the universe at its smallest scales. And its rules are bizarre. In the quantum realm, solid things dissolve into clouds of probability. A particle like an electron doesn't have a precise location until you measure it. Instead, it exists as a wave of potential, a superposition of being in many places at once. The cornerstone of this weirdness is the double-slit experiment. When you're not looking, a single electron behaves like a wave, passing through both slits. The moment you try to watch which slit it goes through, its wave-like nature vanishes, and it behaves like a particle, picking one path. This observer effect reveals a deep truth. The act of measurement fundamentally changes the outcome. This theory, as strange as it sounds, is the foundation for our entire digital world. Here, then, is the grand mystery. General relativity gives us a smooth, continuous spacetime. Quantum mechanics gives us a chunky, probabilistic world. Try to combine their equations, and you get nonsense. The math breaks down. This isn't just an abstract problem. This conflict becomes real in the most extreme places. At the heart of a black hole, or in the first moments of the Big Bang. At the center of a black hole, general relativity predicts a singularity, a point of infinite density where the laws of physics break down. Quantum mechanics, however, insists that nothing can truly be infinite. For a century, physicists have known that this means one or both theories are incomplete. There must be a deeper, more fundamental theory that unifies them, a theory of quantum gravity. Finding it has been the holy grail of modern physics. The hunt for the universe's source code. The search for a theory of quantum gravity is a hunt for the very source code of reality. For decades, this quest has been almost entirely theoretical, a battle fought on blackboards, because the phenomena it describes are so far beyond our ability to test. The scale at which quantum effects should influence gravity, the Planck scale, is trillions of times smaller than an atomic nucleus. The energies required to probe it directly are astronomical. This experimental silence has allowed two major theoretical camps to emerge. First, there is string theory. It suggests that if you could zoom in on any particle, you wouldn't find a point, but a minuscule, vibrating, one-dimensional loop, or string. Every different particle is just a string vibrating at a different frequency, like notes on a cosmic guitar. Gravity is just another note. String theory is compelling, but it comes with serious baggage. It requires the existence of extra, hidden dimensions of space, and it has yet to make a single, testable prediction. This is where the second major contender enters: loop quantum gravity, or LQG. LQG takes a more conservative approach. It asks a simple question: What happens if we apply the rules of quantum mechanics to spacetime itself? The core principle of quantum mechanics is that things are quantized, they come in discrete packets. Light energy comes in packets called photons. LQG proposes that space and time are also quantized. It suggests the smooth fabric of spacetime is an illusion. At the Planck scale, space isn't a continuous sheet. Instead, it's a dynamic network of interconnected nodes and links, a spin network. Each node represents a fundamental atom of volume. The links between them represent quanta of area. Imagine the universe not as a smooth canvas, but as an incredibly fine piece of chainmail. From a distance, it looks smooth, but up close, its woven structure is revealed. This idea has profound consequences. If space is made of indivisible chunks, you can't squeeze anything down to an infinitely small point. The singularity at the heart of a black hole disappears. Instead, matter would be crushed until it reached a point of maximum density and then bounce. The Big Bang might not have been a beginning, but a big bounce from a previous, contracting universe. But like string theory, LQG has suffered from a lack of experimental evidence. The atoms of spacetime it predicts are so mind-bogglingly small that observing them directly seemed impossible. For decades, both theories were stuck. There was no way to tell which, if either, was correct. Until, perhaps, a discovery like the one we are about to imagine. A hypothetical breakthrough. A jitter in the void. Let us imagine a breakthrough. Let's travel forward in our minds to the year 2026. It doesn't come from a colossal particle accelerator, but from deep underground, in a lab shielded from the slightest tremor. The experiment's goal is already impossibly ambitious: to see just how large an object can be forced to obey quantum mechanics' strange rules. This is the hypothetical macroscopic quantum coherence, or MQC, project. For years, physicists have performed the double-slit experiment with larger objects, electrons, then atoms, then molecules. The MQC experiment is the next audacious step. Let's imagine a team has spent a decade perfecting a technique to isolate a microscopic crystal, a fleck of sapphire containing billions of atoms, and cool it to within a hair's breadth of absolute zero. Their goal is spatial superposition. To make this crystal exist in two separate locations at the same time. Using lasers, they gently nudge the crystal into a state where its wave function splits. They hold it in this fragile state for a fraction of a second, then allow the two parts to recombine, looking for the telltale interference pattern that proves it was in two places at once. The challenges would be immense. The slightest interaction, a single stray photon, would collapse the superposition. The lab would have to be an engineering marvel, a fortress of solitude. In our imagined 2026, they finally succeed. The data comes in, and the team is jubilant. They have placed the most massive object in history into a quantum superposition. But as they analyze the data, they notice something strange. An anomaly. The interference pattern isn't perfect. There is a faint, but persistent, jitter in the data, a form of noise they had never seen before. The team spends the next 6 months trying to hunt down its source, checking every system, but the jitter remains. The breakthrough moment comes when a junior researcher decides to correlate the noise pattern with the lab's motion through the cosmos. And then she sees it. The noise isn't random. Its character changes slightly depending on the crystal's motion relative to the ancient afterglow of the Big Bang. The team would be stunned. Having ruled out all known sources of noise, they are left with a phenomenon that looks as if the very fabric of spacetime is interacting with their experiment. The leading hypothesis, the one that would make the hairs on their arms stand up, is this. The crystal, because it is both massive and in a state of quantum coherence, is acting as the most sensitive gravitational probe ever created. Its wave function, smeared out across two locations, is feeling the underlying structure of spacetime itself. The jitter isn't a flaw, it's the signal. It is the signal of the crystal's wave function interacting with the discrete, granular nature of space. Imagine dragging a fine silk sheet over rough sand. The sheet will not glide smoothly, it will jitter as it catches on the individual grains. The team at MQC would believe they are seeing the quantum equivalent of this. The wave function of their crystal is the silk sheet, and the granular structure of spacetime, predicted by theories like loop quantum gravity, is the sand. This slow correction of understanding would tell an important story. For months, they would have tried to make the signal go away, convinced it was a bug. The moment they realized it wasn't a bug, but a feature of the universe itself, would be terrifying and exhilarating. The hunt for quantum gravity, for so long a purely theoretical exercise, would suddenly have become an experimental science. The implications of a granular universe. A discovery like this would be like finding the first Rosetta Stone for the language of reality. It wouldn't provide all the answers, but it would suggest a fundamental truth about the universe's structure. The rules of existence haven't been broken, but the rulebook would be turning out to be far stranger than we ever imagined. The first profound implication is the death of the singularity. In Einstein's universe, the center of a black hole is a point of infinite density where physics ceases to function. But a granular spacetime changes everything. If there's a fundamental unit of space, you can't crush anything down to an infinitely small point. Space itself resists. This gives birth to the idea of the Big Bounce. The Big Bang may not have been the beginning. Instead, a previous universe could have collapsed back on itself, but instead of hitting a singularity, it was squeezed to a maximum density, and then bounced into the expansion we see today. Our universe may be one in an endless cycle, a cosmic phoenix reborn from its own ashes. The same logic applies to black holes. Instead of a singularity, there might be Planck stars. Matter that falls in would be compressed to this ultimate density and rebound, making the black hole a portal that, over unfathomable timescales, releases everything it ever consumed. Beyond cosmology, a granular spacetime forces us to reconsider the nature of time and motion. If space is a series of discrete steps, does that mean time is too? Does an object moving from point A to point B actually perform a series of tiny jumps? Motion would be more like a character hopping between squares on a chessboard than gliding smoothly. Reality would be fundamentally digital, not analog. There's also something quietly humbling about the possibilities this opens up for cosmology's greatest mysteries, dark matter and dark energy. What if they aren't new substances at all, but emergent properties of quantum geometry? Some physicists speculate that dark matter might be an illusion caused by the way quantum spacetime alters the gravitational field around a galaxy. Dark energy might be a manifestation of the universe's own quantum energy, a tiny, residual springiness in the fabric of spacetime itself. And then there is the far future. If spacetime is a physical fabric, can we one day learn to manipulate it? If we could interact directly with the loops of the spin network, could we reweave the fabric of reality? Could we create wormholes or achieve faster than light travel? These ideas are, for now, speculation. But a discovery like the one we've imagined would transform them from idle fantasy into plausible research goals. We would have moved from thinking of space as a fixed background to seeing it as a programmable system. We don't know the programming language, but for the first time, we would know there's a language to be learned. CTA. If this journey to the edge of an idea has expanded your universe, consider liking the video and subscribing to the channel. We are constantly exploring the frontiers of knowledge, from the infinitely small to the infinitely large. And I have to ask, what do you think a discovery like this would mean for our future? What would you do if you could bend the rules of existence? Feel free to share your thoughts in the comments below. Conclusion. We began with a mystery, the profound conflict between general relativity and quantum mechanics. We saw how this pointed to a deeper layer of reality, a quantum realm of spacetime that was, for a century, beyond our reach. We journeyed in our minds to a lab buried deep underground, where scientists, in a hypothetical future, stumbled upon a faint, inexplicable jitter in their data. That imagined jitter changes everything. It is the whisper of a new reality. The first tentative signal from the universe's underlying operating system. The discovery that quantum geometry could bend the behavior of matter would not provide us with a final theory of everything. Instead, it would throw open the doors of perception, replacing one mystery with a dozen new questions. Are we living in a big bounce? Are black holes portals? Is time a series of quantum ticks? We now stand at a new dawn in our quest to understand the cosmos. The map of reality has been redrawn. We are no longer just living in the universe. We are, for the very first time, beginning to read the code it is written in. The rules of existence haven't been broken. They've just been revealed to be more subtle and more beautiful than we ever dared to imagine. And the story that this code tells is only just beginning.